Alright, hell yeah. So we have material mechanics, and we're going over plane strain. This will be the first plane strain problem that goes through all of the equations, because we need to know the principal strains and then the max shear strains on these elements. I guess the only thing that this problem doesn't have is just rotating to a particular angle, but that's fairly straightforward. Okay, so hell yeah. So this is Material Mechanics. This is the book of gear. So booyah. Alright, hell yeah. And the whole point of this video is that you make a structure and then you put an electronic device on it. This it can be very small, up to 1/8 of an inch, you know what I mean, in smallness. And so this is a Rosetta, electrical rosette. Rosetta, they call them, a strain Rosetta, and heck yeah, you just put electricity through them, and if you load up the bridge, you know what I mean, the little wires in this are going to lengthen, and if they do lengthen or shorten, their diameters are going to reduce or increase, and that's going to cause electrical resistance, and that electrical resistance is very, very sensitive, so we can for sure know the change in length just by the change in diameters, or the change in resistance of those wires. So that's pretty sweet. And you can even put them like on a pop can. So it's just kind of good to understand the general gist of why we're doing these problems, because these problems for plane strain are typically always, hey, we have used a strain gauge and we have gotten values. And so these values are going to be like in the X, Y, and then the normal strain direction. So if we have some sort of element, we know that it can change length in the X direction, the Y direction, and then shear in the XY plane is a rotation this way. And we just kind of fix one of fix the base, and we just say that's rotation, even though it actually would kind of rotate, you know what I mean, about a center. You know what I mean, when you do have rotation, it's pure rotation. So that's what this strain is. All right, hell yeah. So again, this is the first video where we can go through all the proofs. And so it just says, hey, we have a well, let's read it. The strains for an element of material in plane strain. I guess there's a figure that goes along with it, whatever. But we have alright, hell yeah, I didn't know this had a diagram. So there you go. So this is what's happening this is going to be an element. Now they're just going to call it a dimension of 1. This is dimensionless, you know what I mean, because we're still talking about an infinitesimal element. But if we make it a dimension of 1, the reason why that we can say this is the change in length is because strain, by definition, is change in length divided by the initial length. If your initial length is 1, then strain is change in length divided by a length of 1, and therefore strain is just you know what I mean, equal to or equally proportional to the change in length. And so that's how we can just have this. So that's how the most convenient way to show this. Now again, our gauge showed that these are the 3 values. These values are going to be very small. It's going to be a change. Strain is a change in length per the initial length. So we're talking a very small change in length, 0.000480. So if I move this decimal place 6 times to the right, 1, 2, 3, 4, 5, 6. And so you just get used to seeing a number with 3 digits times 10 to the negative 6. That's going to be 0.000480. Hell yeah. And we do 10 to the negative 6 just because now we have something to compare. So strains are going to be usually 3 digits. If they get into 4 digits, you know, for steel has a max strain of 0.02. So if we did that 6 times 1, 2, 3, 4, 5, 6, steel would have 2,000 times 10 to the negative 6. So that's kind of the range. These strains can be anywhere from 0 to 2,000 if it's metals like steel, and you're not reaching this number, because this is the number that would cause, probably tend towards failure. So we want to make sure that number is not near the max number acceptable for that material. All right, hell yeah. So this is kind of just the values on these. So for this problem, and what this picture is showing, this is just a generic picture showing positive strain. So I'm going to take, and all these are superimposed on top of each other. So if I say that this is going to change in length in the x direction, it did that. Okay, if I just started out with saying it changed in length in the y direction first, it would do this. Cool. Now let's say I just wanted to say it changed in angle. Shear strain is a change in angle. And so if it changed in angle, this block would just be over here, that same amount on this side. So that's what would happen. And that would be that angle. Okay, now when we combine them all together, I think maybe the simplest thing to do is strain it into the x. So we're gonna lengthen it this way. So now this point is going to be right there, and the shape's going to be right there. Then we're going to lengthen it in the y direction. That's going to be due to the strain in the y direction. So now this shape is going to be all the way up here. And then we can rotate it with this angle, and then that's going to be our final shape. But you don't even have to do it in that order. You could do this. You could have this element and then change its angle first. So this angle will go to there, this angle will go to there, and now I have this element that was deformed due to that shear strain, just that change in angle. And now I'm going to take this, and now we're going to strain it in the x. So this point is going to go proportionally into the x due to this length, as well as this point is going to go proportionally change in length over here due to this initial length. And so because rotating it doesn't change these dimensions, then these initial lengths stay the same. And I think, I don't know if there's, I would imagine that this is 100% accurate when you just take this angle and just rotate it that way. But maybe not, because these lengths stayed the same when we did that. And now our new shape is out here because of that strain in the x direction. When we go up into this direction, we have showed that, hey, this value, I think we're good. Even though that this length increased, well, hey, this length right here is the initial length for when we calculate the strain in the y. So this point will move up to there due to the strain in the y. And then, we have all this material. This is the initial length of 1. And this point will strain up to there. And because, so what we did was we rotated it first, and then strained it into the x. So now we got this shape, and now we're straining it in the y, and we're going to go up to there. So all these points are going to move up to there. Yeah, I don't know, actually. I don't know if I'm picking up a little discrepancy, because if I move this point up to there, the angle is going to slightly change. So yeah, but because these angles are so small that I don't know if this is an approximation where you just fix the angle. I don't think it is, but I'll have to that won't be for this video. But hell yeah, they superimpose on each other. But I think I am picking up a little bit of discrepancy, or I'll have to look into that. I think that's one of the most difficult things about material mechanics, is to figure out what things are 100% accurate and what proofs come from like small angle approximations where they're just approximate but they fit the model when your changes in lengths are really small. Alright, hell yeah. So now let's start to solve this problem. And we're not gonna we're not going to have any predetermined equations. We're going to have to get the transformation equations, but we're going to try to derive them on our own. And so hell yeah. So this is what's happening in the x, the y, and then the shear in the xy plane. Hell yeah, so let's just start in, because I really want to get to those principal strain, those max, the principal strains are going to be the max and minimum strains in of this element at some sort of angle. And then the max shear is going to be at an angle that's just 45 degrees different than that. Okay, so we still need to have a diagram, and this is the one that I use. I do an XY, and then I do an element. The text will do an element that's rectangular, and I think that's useful, and we're going to say this is a differential element, dx and dy, and then we're going to rotate it. We don't have to rotate it through this corner at all, but just, just so our lines don't heavily overlap. And we're gonna, I differ from the textbooks. I'm gonna maintain that this distance is still dx. All I did was rotate it. This distance is dy. Because I know only the strains in the x direction and the y direction and then the rotations, what I do is, box this in. Because I'm real curious about, if I rotate it up, I really want to know the strains in this direction. I want to know that value. You know what I mean? So if this is the initial length dx, this is associated, this change in length is the strain in the x prime direction. This is the x prime. This is the x prime, y prime axes, and this is the angle. So this change in length in this direction is associated with the strain in the x prime direction. This actual change in length in the x prime direction is equal to, well, here's strain is change in length divided by initial length. So change in length is strain times initial length. Hell yeah. So that's going to be, this change in length is going to be the strain in this x prime direction times the initial length is just dx. Cool. And that's kind of what I want to know. And this value should be a function, and so this strain should be a function of the angle. I just want to choose any angle. You know what I mean? I want to choose any angle and then find this value. And what I want to do is compare it to this value. And I want to know when the strain in this x direction, wherever I choose it to be, I want to know when that's the biggest value, and I want to know when it's the smallest value. Smallest value might be negative. It might be a negative, substantially big. This would be the smallest value. This would be the biggest value. Now, hell yeah. And it's funny from the equations, just like what has to be true and what just kind of falls out is like, well, obviously there's going to be an angle where we're going to get the biggest value for the strain in this direction. It just happens to be that if we get the biggest positive, strain changing like this way, at that angle, we're actually going to get the biggest negative strain that direction. So that kind of falls out. Okay, sweet. So to get the equation for the strain in this x prime direction, I definitely need to know the change in length of this element. You know what I mean? So here's our element right here. We have a dx, and I'm going to say this was the dy. Sorry, I drew too many lines. But hell yeah. So this is my rotated element. And if I knew the change in length, of this line to there, then that would be the change in length of the whole element. And then I know the initial length, and so I would therefore know the strain in that direction. Okay, so the change in lengths can be the superposition of the strains in the x, strains in the y, and then the rotations. And so how we do this is since we box this in, I'm going to know that this box is going to strain in the x direction due to this. So this change in length is going to be strain in the x times the initial length in the x. So I'm gonna erase this because this was my original dx to there, that original shape, and then I rotated it up. So if this is dx, this boxed in shape will have dx sine theta and then dx cosine theta in lengths. So this change in length is going to be the strain in the x times the initial length, dx cosine theta. Now, that's not the change in length of this diagonal, which is this rotated element. That's just this. I need to make this into a hypotenuse and then drop it down by keeping my coordinate system with this x prime, y prime. This is the hypotenuse. I'm going to put the angle here. That's where I introduce, like, if I have a horizontal and a shallow angle, like this is my theta. So I'm going to call this the bow tie method, because now I want to know, I want to know if I have a perpendicular coming in, how is that related to this vertical? So what I do for my right triangles is say if this is theta, this is phi, and so a bigger triangle would be, if I can write these in, if that's theta, then I can know the complementary. I'm just going to say theta and phi are complementary angles. And so if I know theta and I have a right triangle, I know the other one is phi. So hell yeah. So right here I know that this is a 90-degree triangle. This is theta, this is phi. I know that if this is a perpendicular to this line, this is a 90-degree angle. So then this is theta. Hell yeah. If this is theta, just by mirror image, this is theta. And then so I have from the horizontal, this will be theta and this will be theta. And then from the vertical, this will be theta and this will be theta. Because these will just get real small, and there's a lot of different ways to figure out what this angle is. But this is the hypotenuse, and I'm dropping down my 90. So for this, I know my change in length is EX, strain in the X, and then times this initial length, which is dx cosine theta, and then it's going to be the cosine component. So sweet. So I know that the overall strain in this direction is going to be the change in length in that direction divided by the initial length in that direction. The initial length would be dx, and this change in length will be the superposition of the strains in the x, the strains in the y, and the rotations. So the faster you can do this process, the better. So we have ex dx cosine theta squared. And then the next one, we're going to take this element and have a positive strain in the y. This is going to be kind of my hypotenuse. This is strain in the y times the initial length, which will be dx sine theta. I'm going to draw in my rotated axes. If this is the hypotenuse, this is the right triangle. And look at this. We have this vertical, so that's theta, that's theta. And so what I'm interested in is this length right here. It's going to be the sine component of that. So the change in length is going to be ey dx sine theta squared. Okay, and then when we rotate this element, we're going to have an angle change. So I'm just going to go to there and there. And this length, this change in length right here, you have to use I use radians times radius is something normal, and that's arc length. And so we have radians, angle in radians times a radius is equal to arc length. Now, this arc length should be a curved line, but we're saying that these angles are so small that we're just doing a straight line and assuming that this radius right here is equal to, even though that this line is longer, this is radius plus a change in the radius. We're going to say those are the same, and it's not a curved line either. And this arc length, so yeah, we're just going to use this radians times radius is arc length. Yeah, and I think to spell this out, because like let's say we do have this shape, it looks like that's a 90, you know what I mean? So cool, if I'm going to say this is my radius and I want to know that length, well, that's not even the hypotenuse. This is the hypotenuse. And if this is the angle, you know what I mean? And I want to know this, well, that would be tangent theta is equal to this length. We'll call it S, divided by R. You know what I mean? So if I wanted to know S, I would say S is R tangent theta, which is R sine theta cosine theta. But when angles are small, this goes to 1, and we got R sine theta divided by 1. And then also sine theta, when the angle is small, if this is in radians, is just the angle. So we have arc length is R theta. You know what I mean? So it is good to go through that process, because the small angles, that's going to mess your mind up if you're not fully confident that, hell yeah, these angles are so small that this length right here is just radians times radius. So let's talk this through. This length is a dx sine theta. You know what I mean? It's this length right here. Sorry, I already increased the length over here. So yeah, this original box was right here. And let me repeat that. The original box was out here, dx dy. I rotated it up here. This box is what I'm interested in. So never lose sight of that. We're still trying to just find the strain in this direction of this rotated initial box dx dy. But the only way we can do that is to, and definitionally, the change in length of this line would be that strain. That would be the change in length of this rotated box. And so to get the change in length of this line, we have to box it in, because we only know strains in the x, strains in the y, and then rotations about the xy plane. You know what I mean? Rotations about, this is a 90 degree, and positive xy strain means that this angle gets reduced by this value in radians. So that's why we have a positive strain. We're just assuming this is a negative, but we're just doing the equation for positive. So we're just assuming positive, but once we get the equation, we'll throw in the negative values. All right, so sweet. So we have the strain xy. And I want to know, and so it's this length right here, you know what I mean? Because this is the box we're interested in, and that length right here is radians. That's the angle. This is an angle in radians. It's dimensionless. These are dimensionless, but this is change in length divided by initial length. This is radians, but it's very similar, and we can take a look at that in a moment. But radians times radius, so we have gamma xy times dx sine theta will be this change in length. And if this box rotates that way, this diagonal will have to be right there as well. And that's the other aspect of this that I didn't really go over, is that if I have a box and here's my diagonal, and I strain it in the x direction, the diagonal still is at the corner and the line still remains straight. If I take this box and then strain it in the y direction, this diagonal will hit that. And then if I take this box and then strain it in this direction, this diagonal, this corner will be right there. And then so this is the final location. So in that process, hey, this diagonal moved 3 different places, but then the accumulation of them is the total. So I could just say, hey, the change in length of that diagonal is that length right here, and then the initial length was that length. So that's kind of what we're finding. And this angle for sure changes. But due to being at a small angle, we're just always saying this angle theta is the same, even though we do move a little bit. And so that's the small angle approximation. All right, hell yeah. So we have this box rotated to here. This is my hypotenuse. You know, this and this new diagonal is right here. The change in length of that diagonal is, you know, drop down a right triangle. This is the hypotenuse. This is theta from that bow tie method. And we're interested in the cosine component. So we're going to have the cosine component of this. So we have gamma xy dx sine theta cosine theta. That's finally the change in length in the x prime direction due to those. And the initial length was just dx. So the dx factor out, and now we have our strain equation. Strain in the x, cosine squared theta, plus strain in the y, sine squared theta. They're all positives. And then so this, you know, just doing this proof 1,000 times, you can kind of just get faster on saying, well, yes, I know they're positive. And how do I show that I know they're positive? Is, well, just choose an element. You know what I mean? So we're going to take this element, we're going to rotate it up to here. And how do you do this fast? I'm interested in this line right here. And so we're going to positive shear it that way, positive strain it that way, positive strain it that way, and then due to shear, we're going to positive strain it that way. And these are going to be additive. So I'm going to make it go this way, and then that way, and then I'm going to take this entire thing and then make it go that way. So, so booyah. So all of those are going to increase the length. So if I took this little box and I strained it in the x direction, hey, this line lengthens. And now that's my point. Now let's strain it in the y direction. Cool. Now that's my point. Hey, it lengthened to there. And now let's take this new box and then rotate it with that positive strain. And now the diagonal lengthens again. So all three of those, if we have positive these values, then that length, that diagonal length, will always increase. And still, don't think of it as a diagonal. What we did, again, is we had an element, and then we rotated it up to these new, new coordinates. And we want to actually know what's happening to this element in, alright, hell yeah. But all the work that we just did was just for the strain in the x prime direction. We're still not even finding, you know what I mean, this rotated element's change in the y prime direction, or its strain in the x prime y prime direction. So so cool. But this is the first point where we do have an equation. We know the strain as a function of theta, and we got there. You know what I mean? And so, and this is where I'm just going to use what they do in the textbooks. Because if this element is rotated a distance theta, it'll give me the change, the strain of this diagonal, which is the strain of this rotated shape. If I rotate this element all the way to theta plus 90, now this element is looking like this. And this is my x prime, this is my y prime. This equation is still valid, sorry, this is the x prime. This equation is still valid for the strain in this direction. Because strain is a proportional, strain is change in length per initial length. Sure, this initial length is less. dy we're just showing is visibly less. That initial length is less. But the change in length will be proportionally less. What will be the same is the value of strain in this direction. So we could have done the same analysis over here, and you just box this in. You call this dy, this diagonal dy, you call this theta, and you call this dy sine theta, dy cosine theta. And you say a positive positive strain in the x direction. You know what I mean? You can even go this way to show positive strain. Positive strain just means that it's getting bigger. So I can bulge it out this side. And then same thing. This is strain in the x times the initial length, dy sine theta. This will be my hypotenuse, do my axes, and then so this is my angle. I'm interested in that. So I'm interested in the sine component. So what we're going to get is strain in the x sine squared theta. You know what I mean? That value. If I did it in the y, you know what I mean? This is going to be strain in the y, dy cosine theta. And I'm just interested in, and if this is my theta, I'm just interested in the cosine component, hypotenuse. And so I would be interested in the strain in the y cosine squared theta. And then if I take this and do a positive shear on it, well, now this actually reduces. Like this lengthened, this will actually reduce the, so I'm going to have a negative right here. And I'm going to, this value is going to be the shear xy, radians times the radius. And so we're going to have shear xy, and it's going to be dy cosine. So we're going to have that cosine component. And that's going to be the hypotenuse. I'm interested in just this lengthening. It's a shortening, and this is theta. So it's going to be a negative this sine theta. And so sweet. What the textbooks do is say, hey, just throw in theta plus 90 into here, here, and here, and here, and then you get the same equation. And how you do that is if I would just choose like a 10-degree angle, 5 to 10, you know what I mean? And then just show what the sine component is, and then the cosine component is of that element. And then rotate it 90, you know what I mean? And then what's the cosine component? Well, it's going to be negative. The cosine component's for sure going to be negative. The sine component's always the horizontal, and that's going to be a positive. Oh, and keep that in mind. If you're taking your angles from a horizontal, the sine component is always vertical. Sine of an angle is vertical. Cosine of an angle is horizontal. And so even if I'm at an angle over here, this is the sine component because that's the vertical component. And this is the horizontal, this is the cosine component. So sweet. So if I had, so this angle is theta plus 90. So if I had sine of theta plus 90, I'd have this value. So we can do that. Sine theta plus 90 is going to be a positive, and it's going to be that value. That's the same value as this, because this is a positive cosine theta. So we're just going to say, hell yeah. Sine theta plus 90 is cosine theta. Now this next one is going to have a sign change, so keep up. So we have cosine theta plus 90. So we want the cosine component of this. That's the horizontal component. It has to be negative. And look at the dimensions. It's the same dimensions as sine theta. But this is a positive value, so we go negative sine theta. Alright, hell yeah. So then all we have to use is this conversion. When we say that this, when we want to solve for strain in the y prime direction, is just this equation throwing in theta plus 90. Well, and why we're doing that is I don't want an equation with theta plus 90. I just want an equation with theta. Because we could have solved, what we were doing right there was just solving it for theta. So how do I take this equation, which is the strain in this direction, and still use theta, but find the strain in that 90-degree rotated direction? And you throw in just theta plus 90. So here I'm going to have a cosine theta plus 90, and that's going to be, so this is going to have two of these. Like that is going to be cosine theta plus 90 times cosine theta plus 90. You know what I mean? That's going to be cosine theta plus 90 squared. This I'm going to throw in a negative sign. And then a negative sine theta. the negatives will cancel, and we're just going to get sine squared. So it's not going to change the, this is still a positive value. Same thing here. But, you know, if I substitute this, where are we at? We're taking this and we're throwing in theta plus 90. Yep, theta plus 90. So theta plus 90 into each of these, where the angle is. So we're going to have sine theta plus 90. And that's going to be cosine. We're going to have two of them. We're going to have cosine squared. Here, we're going to have a sine theta plus 90. This goes to cosine theta. But this one, cosine theta plus 90, goes to negative sine. So we're going to have a cosine times sine, and we're going to have a change in angle. So we have a cosine times sine. And that's exactly what we get. All right, booyah. All right, hell yeah. So I'm going to show you how I do this, because like yeah, that's a lot to do, but still you want to do this kind of fast as. So, you know what I mean? You want to kind of do it from memory halfway. You know, you want the strain in that x prime direction. It's a function of theta, we know that. And so I still would, you know, kind of draw this xy and draw that element, rotate it. I'm just going to say that this is DC, and then this is DS, and this distance is D. You know, so still, we're just kind of so now I'm saying S is sine theta, C is cosine theta, and then you can just do this in kind of such a smaller frame. And I know that the strain is going to be the change in length of this line divided by the initial length. And I know everything's going to be, the D's are just going to cancel. So I can just know that and just kind of move away from that. I know I'm going to have a change in length in this. That's just going to, and then my strain, EX, we're just going to call X. EY, we're going to call Y. And then strain XY, I'm just going to call Z. And then so, I never have to write sine theta again. We're going to do a double angle, so when we get sine, and then s squared is sine theta squared, and so forth. C squared is going to be cosine squared theta. Also, S2 is going to be sine 2 theta. And just S is just theta. You know what I mean? So C2 is going to be cosine 2 theta. Because we're going to do the sine identities, and it's just going to make... This is kind of where I wanted to start the video, to be like, hell yeah. This way, you don't have to spend hours going through a derivation, but you can still, you know, from memory, like, why do I know this is going to be x cosine squared plus y sine squared plus z, you know what I mean, sine cosine? You know what I mean? So that is just so fast, and we know that because, hey, I'm going to strain in the x, and so we're going to say that's going to be, you know, it should be, well, this is going to be x cosine, hell yeah. So this is, you know, it's going to be actually xd. X is my strain. The initial length is dc. But I know I'm going to factor out all the d's. You know what I mean? So hell yeah. So we're just going to do xc. And then I know I need this change in length right there. That's the cosine of that angle. So I see xc squared, x cosine squared. Now the strain in the y. I know it's going to strain this direction. And, alright, hell yeah. With this picture, I always mess up, let's see. So this was the box, and then this is the rotated box. Yeah, so this is the diagonal. That's where it used to be. We strained it in the x. We got that initial, you know, that extra length. We're going to strain it in the y. And this is my, this vertical is going to be y. You know, it's going to be y sine. You know, it's going to be the strain in the normal strain in the y direction. So again, y is the normal strain in the y direction, times the initial length, which is ds. I'm just going to call it s, because we're going to factor out the d's anyway. And that's going to be this. And then using that bow tie method, you know what I mean, I have that. And I can just really see these angles just real fast. Be like, hell yeah, there's my horizontal. there's my hypotenuse, y sine, and then I'm really interested in the change in length. Oh, and so I even need to, if this is my horizontal, you know what I mean, draw my axes, and hell yeah. So I'm interested in the sine component of there. But yeah, it's interesting how you can draw these real small and still kind of keep up. So hell yeah, so that's going to be y sine squared. When I rotate this one, radians times radius, this is going to be z s, and then this length that's over here, and it's going to be the cosine of that angle. So ZSC. CSC. Hell yeah. And now once I got it here, you know what I mean, I can even do my angle identities. We're going to need two of them. This is going to be theta and theta. And again, my convention is if I'm saying this is theta, and I got, you know what I mean, I'm just saying that this is theta. So this little thing is equal to theta. Hell yeah, so I got a theta and a theta. I'm going to do the cosine. So this value right here, this is 2 theta. That angle is, you know what I mean, well, that's a bizarre way. But that angle right there is 2 theta. With the cosine identities, you know, I mean, what we're, and I got these memorized now, so that's good. So cosine squared is, and I'll write it out once. Cosine theta squared is 1/2 plus 1/2 cosine 2 theta. And then sine squared theta is 1/2 minus 1/2 cosine 2 theta. So we're going to show those, but this is the fastest way with the least amount of strokes of the pen. And you can kind of work in a small framework. So hell yeah, this length right here is cosine 2 theta. And so see how I can just really simplify just C2. And how to do this proof is you're saying this is the hypotenuse, this is the cosine component, and then drop it down again. This is the new hypotenuse. Like this hypotenuse is 1, so I'll spell it out. This hypotenuse is 1. This length right here is cosine theta, 1 cosine theta. This now is my new hypotenuse, and I'm going to take the cosine of that. And so, hell yeah, this length right here is cosine squared. We overshot it. We need to subtract, and that's where this one is a sine. This is the sine. This is 1 sine theta, or just sine theta. And then we just need to know, you know what I mean? Hey, bow tie method is like if, well, and then I definitely use this. If this is theta, that is the complementary. That's phi. So a lot of different ways to know that this vertical, well, and this is perpendicular. So again, the way to you know, if I have this, and this is theta, and this is theta, and then I have a perpendicular to this, you know, so I'm going to have a vertical, and I know that this is the perpendicular. I know that this, let's say this slope right here is negative. I know that the perpendicular has to have a positive slope. And if, now I might just be, I don't know if I want to say anything more. I just don't want to say wrong stuff. But hell yeah, I don't know. I mean, the one way that I like to look at how that angle is theta is if this is a 90 degree, if I just brought it down here, there would be no angle. And then if I pivoted it up and then shoved it into place, that angle that I rotated is the same. You know what I mean? So I might just leave it at that. But hell yeah. With this proof, you really need to know that that vertical angle is theta. What's another way? So this right here, this angle right here has to be the complementary. And then, yeah, I don't know. Yeah, what's the easiest way to know that that's theta from another perspective? I don't know. I really don't care. But no, I do care. But my mind is blank. So yeah, it's just interesting. I just know that and that's the whole that is the bread and butter of figuring out this proof, is like, what's this little length? Well, this is sine theta, and this is the sine component, so that component right there is sine squared. So the whole idea is this length right here, cosine 2 theta, is cosine squared minus sine squared. Booyah. And, you know what I mean? I want to know what cosine squared is all by itself. And so what we're going to use is Pythagorean's theorem. If this is theta, this is sine, this is cosine, this is 1, then this squared plus this squared is equal to that squared. So we got sine squared plus cosine squared is equal to 1. Hell yeah. And now, you know, we can rearrange this 3 different ways. Sine squared is 1 minus cosine squared. Cosine squared is 1 minus sine squared. And then just always know that if you're trying to find one of the sides, like Pythagorean's theorem says, if you're trying to find one of the sides, you're always taking the hypotenuse minus the other side. Because if you're trying to take the hypotenuse, if you're trying to find the hypotenuse, it's always the side squareds added to get the bigger number. But if you already know one of the bigger numbers, the hypotenuse, and a side, you always have to take the hypotenuse squared minus the side. So that is the visual light bulb, you know what I mean, that goes on in my head all the time. So if I want to know the side of a right triangle, I'm going to say this is the hypotenuse minus the other side of that right triangle, and then minus s squared. So hell yeah. So now with very little strokes of the pen, we got 1 minus 2 sine squared. Maybe just get this to the other side. So we have our sine squared is 1 plus cosine 2 theta, and then divide by 2. Sine squared is 1/2 plus 1/2 cosine 2 theta. And booyah. So this is our proof, you know what I mean, just in expanded form. And so, hell yeah, we're going to do that same thing with solving for cosine. So cosine 2 theta is cosine squared minus, now sine squared is going to be that hypotenuse squared, 1 squared, minus the other side, cosine squared. Now we do have, this is the negative of that, so we're going to have minus 1 plus cosine squared. We're going to have 2 of those. So just in a hell of a lot of steps, we're going to have 2 cosine squared minus 1. Let's get this to the other side. So we have negative 2 cosine squared is equal to negative cosine squared minus, well, that was just the dumbest way to do it. I mean, obviously, just maybe get this. From here, I would just get the negative 1, add it to the other side. So we have cosine squared plus 1 is equal to, whoa. My bad. See, I even this right here is cosine 2 theta. But anyway, so get the 1 to the other side. We'll have cosine 2 theta plus 1 is 2 cosine squared. I hate when I get more negatives. You know what I mean? Because what do you do here? Do you have to just, you know, multiply each side by negative 1? Hell yeah, you do. And you got 2 cosine squared is equal to, I'm just going to rearrange these. 1 plus cosine squared divided by 2. So we have cosine squared is 1/2 plus 1/2 cosine. And again, I munched it because, holy Toledo. Let's just scratch all this. Yeah, I'm going to run into issues with this cosine 2 theta versus cosine squared, especially on this identity. And so, sweet. So this is cosine 2 theta. I really want to solve for cosine squared. Get the 1 to the other side, but I really want to solve for this side. So I'm just going to flip the sides. And this is cosine 2 theta plus 1. Sweet. And now I can divide by 2. And I'm even going to rearrange the order of this. 1 plus cosine 2 theta. And now divide by 2. Cosine squared is going to be 1/2 plus 1/2 cosine 2 theta. And then there is my proof. There's my identity there. There's my identity there. I need to get a new pen. Alright, hell yeah. and the reason we're doing this, like right now, we could literally, well, could we solve the whole problem? Well, we would need at least one more equation. You know, we would need the shear strain equation. So I guess this problem, we're just kind of doing it from a proof perspective. But yeah, even right here, this is the strain in the x prime direction as a function of theta. So you can plot that and just find the largest values, you know, just from that equation. We're going to use it, we're going to try to do the derivation, because we know maxes and mins happen when the derivative of this, we're going to take the derivative of this with respect to theta. You know, we're going to change theta. This is plotting from negative 90 to 90. And at some value of the angle, we're going to get a maximum. And now the red line on here is the one that we're solving for. You know what I mean? So the maximum is going to happen right there. It's going to happen at like a negative 16 degrees or something. And we'll see. This problem might be slightly different than the one that number-wise. But let's see. A is, yeah, it's going to be slightly different. Slightly different numbers. Okay. So we're going to take this. And this is a function of cosine squared and sine squared and a sine times cosine. So differentiating that's a nightmare, where once we plug in this, we're just going to have a cosine 2 theta. And besides just a u substitution, where you have the derivative of cosine 2 theta, just becomes 2, you know what I mean, negative 2 sine 2 theta. I mean, it's just cosine changes to the sine. Make sure you know if you have a negative positive out here, and then you just have a 2 in front from that u substitution. So hell yeah, I'm not going to go over the u substitution of that. We might though, because this video, obviously, I'm always curious to do like shorter videos, but like, why not do that? I mean, that the whole algebra is where you're going to get caught up, you know, when learning new things. So let's see what we do. So hell yeah, so we're just going to sub in these trig identities for this. So we're going to have x, and then we have this identity, 1/2 plus 1/2 cosine 2 theta. Then we have y is 1/2 minus, oh bummer, one of these should have been a minus, and it should have been this one. Let's take a look at this. So why did we mess this one up? We had cosine 2 theta. Yeah, I mean, to get this by itself over there, I would get 2 sine theta. I would add both sides by that. I hate that term, but just get it over there. And it's going to be positive over there. And then get this to the other side, and that's going to be negative. So 1 minus cosine 2 theta. And then divide by 2. So sine squared is going to be 1/2 minus 1/2 cosine 2 theta. And let's spot our errors. You know what I mean? I think that I got that to the other side, but then when I got this to over there, hell, I did not make it a negative. So there was my error. We caught it, and this is the one that has the negative in it. And so yes, so this was right. You know what I mean? My guess. And it's just good to be like, hey, do you remember? Because that's what I'm also like. I really love the proofs, and like, hell, let's go down that 15-minute path of deriving that identity and making sure we can do that every time. Like, do that 20 times to where you're just like, I've done it. You know what I mean? That's what you should do with trigonometry. And that's kind of my strategy. Now, sometimes it can be so tricky that you might have to, it might be like a 3-hour, 4-hour problem, because you're always going to make a mistake halfway or at a certain juncture where you're just like, ooh, I don't know why I'm making that mistake, or I'm not seeing what's happening. But yeah, that's a perfect opportunity to do the proof. And if you do the proof at least 10 times, that's when I start to just memorize the equation and be like, well, why don't I just memorize? Because even this is probably about the 20th time doing this, or more. And then I'm just like, well, haven't I memorized this yet? But I refuse to just memorize things early. So on this, like the last coincidence that I will memorize is the fact that this is positive and this is negative, and which one is positive and which one is negative. But then it was useful because then when I was trying to figure out what this one was just right off the bat, it was like, well, this one's the positive one and this one's the negative one. So sine squared is 1/2 minus 1/2 cosine 2 theta. Plus, and now we have our next identity. Draw a fairly wide angle, bisect it, theta, theta. And then, hell yeah, this is just a hypotenuse of 1. What we're interested in is this. This is sine 2 theta. You know what I mean? This is the sine of that angle when the hypotenuse is 1. To do this one, do your cosine. That's going to be this. That's cosine theta. And then do the sine of that. So if this is the new hypotenuse, the sine of that is that length right there. So this is cosine sine. And then just do the opposite. This is the sine. This length is the sine. This is the angle. And then this is the cosine. So this is sine cosine. And then those two add to make that. So we have sine 2 theta is sine times cosine plus cosine times sine. By convention, it's good to write it sometimes like this unchanged, at least to show that step. And then just by convention, we're going sine times cosine plus sine times cosine. We got two of those. You know what I mean? And this is even just like, well, throw a generic 1 out in front and call these oranges. You know what I mean? Hey, we got one orange and one orange. Let's add them together. Hey, we're going to have 2 oranges. What are the oranges? S sine times cosine. So we're going to have 2 sine times cosine. So hell yeah, to write this one out, sine 2 theta is 2 times sine theta cosine theta. And what do we, so yeah, so we have our identity that sine 2 theta is 2 times sine times cosine. And we just have one of them. So cool. So sine times cosine is going to be 1/2 sine 2 theta. All right, so we're gonna add that in right here. Oh, bummer. Kind of. So anyway, so we're rearranging this equation, and we have, and yes, gamma xy is, we're saying that's z. So we have z, we're going to have 1/2 z sine 2 theta. Okay, sweet. And so let's write this on a new sheet of paper, that we have our new x prime. And x prime is strain in the x prime. You know what I mean? So we're just, and yeah, I should have said that. Yeah, this is just going to be x prime now. X is going to be the strain in the x, y, strain in the y. Z is going to be a strain, shear strain in the xy plane. So sweet. So we're going to have x 1/2 plus 1/2 cosine 2 theta. That's just that identity. What identity is this? It's the cosine squared. And then we're going to have plus y, and then the sine squared identity is 1/2 minus 1/2 cosine 2 theta. And then we're going to have the shear strain in the xy plane, that's z times sine cosine. So that's divided by 2 sine, oh, bummer, sine 2 times the angle. Okay, and so now what we're going to do is take the derivative of this with respect to theta. Oh, not yet. We have to make it a little bit cleaner. Hell yeah, so the textbooks aren't going to show this part. They're not going to show you that, hey, we're going to have 1/2 x. We're just going to FOIL the x through. So we have 1/2 x plus 1/2 x cosine squared plus 1/2 y minus 1/2 y cosine 2 theta. And yes, I said that wrong. This is cosine 2 theta. All right, plus 1/2 z sine 2 theta. And then these two terms aren't a function of theta, so we're going to do 1/2 x plus 1/2 y, and And just in general, I'm just kind of showing you these steps because they're just going to go from here to, well, they're just going to throw in the identities and just really do this. They're going to be like, hey, x plus y divided by 2. So we have x plus y. We're dividing by 2 because they're both functions of the half. And then we're going to have plus x minus y divided by 2 cosine 2 theta. And then plus z divided by 2 sine 2 theta. And so the transformation equation is strain in the x plus strain in the y. And let me say these correctly. Normal strain in the x, normal strain in the y. So this is normal strain in the x direction or x-axis plus the normal strain in the y divided by 2 plus the normal strain in the x minus the normal strain in the y divided by 2 times cosine 2 theta plus the shear strain about the xy plane divided by 2 sine 2 theta. So this is the transformation equation for strain about the x prime direction. This is also, you could write it like this, strain in the x prime as a function of theta. Now for sure we can differentiate this with respect to theta. This is a constant, it goes to 0. So we have 0 plus, and then we have to use u substitution. So so let's go back to our letters. So we're going to have, and let's just take cosine 2 theta in general. If I want to take the derivative with respect to theta of cosine 2 theta, I'm going to say this is the derivative with respect to u. I'm going to say, and then I'm going to do cosine u du d theta. And what this, I mean, still, I guess this is a, oh, how would you do this? I forget, you know, I really want to talk my way through the lingo, but yes, if you have a derivative of something with respect to theta, you can do the derivative of something with respect to u times du with respect to theta. But this function has a theta in it, where this function has to be changed to have a u in it. And so what we do is we just choose what u is. So if we have this derivative, u is going to be 2 theta. And and then you can just go for it, you know what I mean? You could say, okay, now I have this part, you know what I mean? Start just writing it in. I think that might be the easiest way. So I have derivative of cosine of u du, and then I have du d theta. Cool. So I know what the generic derivative of cosine is. So a cosine, and if you want to get technical, do 3 hashes and then 2 hashes. And this is going to be 30, 60, 90. And we'll do sine theta first. This is 0.5 and 1. So at 30 degrees, sine theta is 0.5. It's linear. You could consider it linear all the way up to 60 and then like this. And so if you do that, it's just such a great way to do sine and cosine. So this is going to be the cosine one, this is the sine one. Cosine is going to start at 1, so 30, 60, 90. And just linearly, it's going to look like that. You know what I mean? And, you know, cosine, sine of 60 isn't 1, but it's 0.866. It's up there. This is very close to 90%. You only get a less than 15% error by approximating that way. And so really, and then the actual graph just hits the tangents, you know what I mean, of that approximation. And you don't even need to do that. You just need to know that, hey, sine theta goes like that, and then cosine theta starts at 0 and then goes like that. And so the derivative is the slope of this line. At 0, I need a function that says 1. Cosine at 0 says 1. And then the derivative of cosine, I need a function that at 0 says slope of 0. Slope is 0 right here. That's sine, but then also know on the cosine, hey, this slope is always negative. You know, even from the get-go, it's 0 to negative something. So the derivative of cosine is negative sine. The derivative of sine is just cosine. All right, hell yeah. So the derivative of cosine is going to be negative sine. So we have negative sine u. So that's that part. What's this du d theta? Well, here's my u, and then I need to take the derivative of this. So derivative of u d theta, which is the derivative of 2 theta d theta. Okay, so that's what we're going to do, derivative of 2 theta d theta. A lot of different ways to do this. I mean, you could just break out the constant, and so we have 2 d theta d theta. You could just say that's an identity of 1, and we got 2 there. You could say this is very similar to the derivative of 2x. Like, still, you're taking it with respect to x. So, yeah, derivative of 2x just becomes 2, just from your local knowledge of that. Here's a good, better representation of that. Factor out the constants, and d theta, because they're same top and bottom on a fraction, that's 1. Cool, so this just becomes 2. And again, we get negative 2 sine u. So there you go. So, you know, a little bit of u sub. Alright, hell yeah. So, yeah, the u sub of this one's going to turn into negative 2 sine 2 theta. This one's going to be positive 2 cosine 2 theta. Hell yeah. And since we don't have too many terms, I won't use my simplification. We'll just go for it. This 2 is going to knock out that 2, but we're going to have a negative. So the derivative of this, and we're going to set the derivative equal to 0. So let's just do the derivative part first. So we have negative strain in the x minus strain in the y sine 2 theta. So this 2 knocked out that 2, and then this negative comes out front. And then this for sure changes. The slope of the cosine graph is 0 at this 0 angle. So I need, sine 2 theta. And it's a negative slope, negative sine 2 theta. Cool. Now this one, these 2's are going to knock each other out, and then we have strain in the xy, and this becomes cosine 2 theta. This is equal to 0. Sometimes I do this. Well, not today. So let's get this. Oof. Yeah, let's do this. You know what I mean? If I don't want to write a whole lot, let's just put the negative sign here and turn this into a positive. You know what I mean? And so, cool. Now my sine's over here, and now let's get the cosine underneath the sine. That's going to be, and that's going to be tangent. If I get this under there, you know what I mean? Can you see how that's tangent? Sine divided by cosine. So we're going to have tangent 2 theta, gamma xy divided by, so we have gamma xy divided by strain in the x minus strain in the y. Alright, sweet. And then, and this, the derivative, setting the derivative equal to 0 must give me a max or min. Alright, hell yeah. So, yeah, we get a max and a min. And this angle has to be a max or a minimum. And so, here's the tangent of this angle. And let's see. Well, yeah. So this is going to be 2 theta. This could either be, we're going to say it's the principal angle, and it could be either principal angle 1 or 2. I think in books they're just going to say this is just principal angle 1. But if we just have it in this form, it could be 1 or 2. because it could also be negative strain in the xy divided by negative strain in the xy minus strain in the y. So having a negative top and bottom. But yeah, let's explore this. So when we have this, you know what I mean? We have if we have a triangle, tangent means that, hey, it's this opposite divided by the adjacent. You know what I mean? So if we have tangent of this angle theta, that's going to be opposite minus adjacent. So we're going to draw this graphically. And so this is opposite is going to be a positive value. So we got a positive value. And then the adjacent is also a positive. So if here's my xy coordinate system, the opposite is positive, xy, and then the adjacent is strain in the x minus strain in the y. And then that means that we have a right triangle here. And then also, you know what I mean, it is going to be negative xy and negative strain in the x minus strain in the y. My material mechanic book, well, I can't call it mine, but what I went to school for, Gear, material mechanic author Gear, just shows you that side of the equation, doesn't show you this side. And so I think that's kind of interesting, where Hibbeler shows you this, you know, shows you that there's two angles. And so this angle right here, though, so no, there is some truth to this. Written like this positive, like this angle is theta p. This is the principal angle 1. The angle associated with this value right here is the principal angle. Now, if we throw in, again, this whole deal is that we're given with our electric strain gauges that we put on bridges and stuff, we're given these three values. These are given in the beginning of our analysis, beginning of the problem. They might be negative, they might be positive. So this ratio could be a negative, it could be a positive. It could be negative up top, it could be positive down below. You know what I mean? It could be negative up top and then negative down below. So with that in mind, yeah, there is... so this ratio, yeah, it'd be fascinating, because what they do is they do this. You know, we are going to find they're going to call this the radius, whether you like that or not. Like, I don't know. You know, I mean, you don't even have to introduce that term if you just know that this hypotenuse, and I guess I'm just going to call it r, is this squared plus this squared square root that. So r is the square root of this, strain in the x minus strain in the y squared, plus the strain in the xy plane, the shear strain in the xy plane squared. And then square rooting that, it does become negative and positive. Alright, sweet. Now I'm going to just kind of bust out some sheets of paper. Alright, cool. So now that we know all three of these values, you know what I mean? I think, yeah. Let's just read, because we're gonna get into this. So we have this equation that tangent of 2 theta principal is the shear strain in the xy plane divided by the normal strain in the x minus the normal strain in the y. And we did a graphical representation of this. Where this is the normal strain in the xy, and this is the normal strain in the x minus the normal strain in the y. Because both of these are positive, you know what I mean? They're on this side. This is the same thing, though, as the top being negative and the bottom being negative. Nothing really changes, except graphically, that's going to be over here. This is going to be associated with negative. And I don't know if that's a redundancy. I never know what to do. You know what I mean? Do you actually say this is negative? You know, are you going to... I think doing that is kind of a cool method where you're just like, heck yeah, this is negative strain in the x minus strain in the y. just to show that, hey, you're saying this is a redundancy. Obviously, this is the positive y direction. This is the positive x. Like, obviously, this is this length right here as an absolute value is just strain in the x minus strain in the y. But I don't know. You know what I mean? Yeah, so throw a negative on there. Cool. And then we know that this hypotenuse, I'm just going to draw it in like this, is going to be strain in the x minus strain in the y squared plus shear strain in the xy plane squared. And I'm just going to leave it as a positive value. If you leave this as a positive value, then, yeah, and we're saying that this is the principal, this is the principal angle that makes this be the max. So we're trying to find the shear strain about a rotated element where this is max, where this becomes max, and we're going to call that the first principal shear strain. We also might want to know the minimum, and that's going to be epsilon 2. The normal, the minimum. This is going to be the minimum normal strain about a rotated element. These are going to be 90 degrees opposed to one another. And again, that's a function of the geometry. And all parts of these derivations are just geometry. We have not introduced any material properties. It's literally just geometry and saying if that geometric shape goes to there and then increases to there and then rotates to there, you know what I mean? And then yeah, so if yes, it's kind of wild. Let's say I glued on a sticker like this, and then I took this shape and stretched it to here, and then did this to it. What would happen to this shape? That's kind of what you're interested, you know what I mean? Then you're like, well, is this shape going to go this way? Is this shape then going to go this way? And is your shape going to go in still that positive direction? You know what I mean? Who knows? Maybe that shape actually goes in the negative direction. And the negative direction here, and then the positive direction. You know what I mean? So now this shape is like this instead of like this. You know what I mean? So that's kind of what we're interested in. And we're interested in, hey, that distance looked pretty max that direction. Anyway, and then we're trying to look for the max values. Okay, from this triangle, we know that, bummer, and this is 2 times the angle. See how this is tangent of 2 theta p1, so I just caught that. And this is where with Moore's circle, and, you know, I'm going to make a factor of 2 error all the time. And so, you know what I mean, beginning of a Moore's circle, a plane strain, plane stress problem, just make sure, you know what I mean, you throw asterisks on the board to double check for that divide by 2 error. Alright, hell yeah. So, and then what's our equation? You know, can we memorize this? I mean, did you remember it? You know what I mean? Because sometimes you don't. So let's see if we can do this from. So our rotated strain is going to be strain in the x, cosine squared, plus strain in the y, sine squared. These are all positive. Shear strain in the xy plane, sine, cosine. And then I'm going to use my trig identities. This one's going to be 1/2 plus. This one's going to be 1/2 minus. So I'm going to have an x plus y divided by 2 plus x minus y divided by 2 cosine 2 theta. See how now I can just kind of do that from memory? And then this is going to be a z divided by 2, and this becomes sine 2 theta. Hell yeah. So, so this becomes normal strain in the x plus normal strain in the y divided by 2 plus normal strain in the x minus normal strain in the y divided by 2 cosine 2 theta plus shear strain in the xy plane divided by 2 sine 2 theta. So this equation is a function of theta. This is going to give me a maximum. And so, this is also, if I throw in, if I say that this is, I think this, don't quote me on this part, but I think this is 2 theta 2. Because I think in the textbooks they do throw a number 1 here for this angle in particular. It doesn't mean that geometrically it's going to be 30 degrees. You know what I mean? This angle could be anything between 0 and 360, just because these numbers could be anything. You know what I mean? Because so check this out. Let's just play a little game. What if this is positive? Okay, that means that the angle is going to be somewhere between 0 and 180, and that's 2. And then keep in mind that's 2 theta p1. Okay. Let's say this is positive and this is negative. Okay, the angle is going to be somewhere between over here. So 2 theta p is going to be between 90 and 180. Now that's 2 theta p. So what would theta p be? Well, that's going to be between 45 and 90. All right, so now let's say this is a negative number, and now we're down here. So our angle is going to be anywhere between 180 and 360. 180 to 360. That's 2 theta p, and so theta p would be that divided by 2. So theta p, if this is negative, is going to be 90 to 180. All right, hell yeah. So, and that's the full range, is that theta 1 can be any angle between 0, yeah, so 2 theta p can be any angle between 0 to 360 degrees. Therefore, theta p, and this could be the first or second, in that case, could be any angle between 0 and 180. Oh, see, and I have that wrong. So the textbook, there is no 2 here. This is the primary angle. Yes, so yeah, that is interesting. And then so I'll have to dive into this, because theta p1 can be any angle between 0 and 180. But what we know is that theta p2 is theta p1 plus 90. Alright, I should write this in. So therefore 2 theta p2 is 2 theta p1 plus 180. So we're just saying that 2 theta p1 can be any number between oh yeah, 2 theta p1 can be anything between 0 and 360. Cool. Well, we're saying though that theta 2 or 2 theta p2 is just plus another 90. So, you know what I mean, if this all the way to like 350 degrees is theta p1, cool. Theta p2 is just plus another 180. And so yep. And then so yeah, I'll just have to double check if dimensionally this, like as a graphic, I think graphically this is theta p1 and then this is theta p2. But just know that this theta p1, we're just showing it at 30 degrees. I think that's what's messing me up. I could just rotate this any way that I wanted to. So this theta p1 could be all the way over here, where theta p1 is all the way right here. We could either call that a negative 10 degree angle or a positive 350 degree angle. And in that case, you know, if we called it a negative 10 degree angle, then plus 180 is theta P2 is 2 theta P2, and 2 theta P2 would be plus 180. That would be 170 degrees. And then the only thing in the end is to be like, cool, we found 2 theta P1 and we found 2 theta P2, but we need to divide by 2, on both of these to get that theta P1. Our principal angle that is associated with our max strain on a rotated element. And this is going to be the minimum. And I've made a mistake. Even going through these proofs, I swear, so the strain in the principal direction, this is always max. Now, it can be a small max number. It can be like 10 times 10 to the negative 6, where this can be hella negative, negative 2,000 times 10 to the negative 6. Still, this is your max, this is your principal strain number 1, this is your principal strain number 2. On a Mohr's circle, this is the positive direction of that rotated strain, and so, hell yeah, this is going to be your principal 1, this is going to be, and let's draw it how I kind of drew it. This is your principal 1, and then hella negative, this is your principal 2. Alright, halfway, and this is going to be the circle. Cool. And this is going to be the positive shear in the rotated direction. Shear strain in that rotated direction. Alright, hell yeah. So I thought I was just going to, just really ace this part, but we had some questions, and now I kind of get it. And then, yeah, textbooks never lie, but it's just like, why are they doing that? You know what I mean? When you kind of just don't know why they're doing something. But hell yeah, I think they're calling that theta P1. Even though if you just get a generic value, if I just got tangent of 2 theta, or just tangent of a theta, and just got a value, cool, I'm going to get an angle associated with that. Or put more plainly, if I took the inverse tangent of this, of that number right there, I'm going to get an angle. Forget that it's 2 theta, but that's going to give me an angle. If I do that right here, I do not know if, so if I just throw in these 2 values, and I get an angle, and that's going to be 2 theta, and so I get that, and I'm just going to divide that by 2. So I inverse tangent this ratio, I get an angle, divide it by 2, and so I'm just left with this angle. Do I know if that angle is associated with theta P1? No, I don't know whether it's theta P1 or theta P2. I don't know which one that is. So that's where they come back to this equation, and they say if you throw in the value of cosine 2 theta from this triangle and sine 2 theta from this triangle, that is going to always give you the max value. So, and how we do that is cosine 2 theta, just cosine in general, cosine of this angle is the adjacent divided by the hypotenuse. So here's our triangle. This is 2 times the angle. So cosine 2 theta is going to be the adjacent, normal strain in the x minus normal strain in the y, divided by this hypotenuse. And that's going to be normal strain in the x minus normal strain in the y squared plus the shear strain in the xy plane squared. Same thing with sine 2 theta. That's going to be the opposite, divided by the hypotenuse. Alright, hell yeah. And if we throw in this value right here is just a number that's associated with those initial strain in the x, strain in the y, shear strain in the xy, just those initial given values. And so if we throw those values into both of these values into this equation, cosine 2 theta, into there, sine 2 theta, into there, it is going to give you the max. And so that geometrically, I don't know where that falls out. or if you did a different proof where you had these two variables, like, you know, but yeah, so that will always generate the max. And I just don't know if that's just from coincidence or from something, because this is a square root. This could be plus or minus, you know what I mean, or whatever, I think. But for this, we're always going to give this the positive value. You know what I mean? So that also comes into this calculation. And so let's do it. You know, I mean, we haven't gotten deep into this problem, and I don't even think I've uploaded the variables into my calculator. We'll see if we have. Hell yeah. So, cool. So for this, we have 3 values. I'm going to enter them into my calculator. So 480 times 10 to the negative 6. And how I like to think of this is just 3 zeros and then 480. Sometimes that's easier, and then just know that move the decimal place 6 times, 1, 2, 3, 4, 5, 6, and we got that value. So 0.3048 stored. I'm going to store this as alpha A. Alpha A and alpha B, and then this is going to be alpha Z. The reason I'm not storing these as X and Y is because in my calculator, I'm going to graph X and Y and solve for X's, and that's going to mess up my X value. So that's what I do. You know, when my graphing calculator will solve a value for X and sometimes for Y, I'm going to have my X, Y values be A and B. Cool. So this Y value, 0.123014, stored as alpha B. This negative 0.123035, stored as alpha Z. So now we got it. And so, heck yeah, we can actually do these. So this is going to be A minus B in my calculator divided by the square root of A minus B squared plus Z squared. Just to show you kind of what I'm doing in my calculator. So we have alpha A minus alpha B divided by the square root of alpha A minus alpha B squared plus alpha Z squared. Cool, and we get a value of 0.697. Over here, let's just do it from the letters that we put in. So we have alpha Z divided by the square root of alpha A minus alpha B squared plus alpha Z squared. Alright, and so we got negative 0.717. Now we're going to plot those 2 points, because what they say is that if we throw in those values, this is going to be max. And so the angle associated with these values has to be that max angle. And so that is where that is the place where I kind of like don't see it 100%. So we're just going to do it a bunch of times and see if we see that. And I feel like I'm seeing a little bit more. Because these 2 numbers are only one location on this coordinate, and if we're taking our angle from this positive horizontal x-axis, then that angle can only be in one place. And so, oh, and then the other thing is, I guess these aren't really, well, how do you say this? If I have a triangle, and this is my angle, this is my sine component. So it looks like the way I have it drawn in the positive. So the vertical component is going to be negative. So we already talked about how from the horizontal, sines are going to be a vertical. So it's going to be down here. And then this is going to be a positive. The cosine component is going to be positive. So we're going to be down here 0.7 and then over 0.6. And so that's going to be that's going to be a hypotenuse where this is 0.7, and they're really close. This is 0.7, 0.717, and then this that's going to be this distance, 0.717, and then this distance is 0.697. So there you go. So we have a negative 0.717 down, and then an over. And then so the angle associated that is this angle right here. And so this is going to be theta P1. And we could figure out what the negative is by doing that angle right here. The negative angle is going to be the inverse tangent of sine divided by cosine. Which is the same thing, because the radiuses are going to cancel each other. That's going to be the same thing as this right here. So this still gives you the maximum angle. Oh, so now I'm curious, because these two values gave me So I'm really curious to see what's up with this. If there's a problem where this ratio and taking the inverse tangent isn't going to give me this graphical angle, where if I solve for these two values, I'm going to get a different angle than had I just plugged it into here. Because if I do this, yeah, and that's basically the only way I'm going to believe that, I know there's two angles here, but there's a 50% chance that you're going to get the right one from this equation. There's a 100% chance you're going to get the right one from this equation. And so what they say to do is, sure, pick off the two equations. You're going to have two angles within 0 and 360. You're going to have a theta P1, one, you're going to get one of these, and then you're going to get the other one rotated 180. You know what I mean? So whatever first angle you pick off up here, the other angle is just the rotated 180 of that. But the way we have it right now is that we chose the right angle popped out of this equation. So we have alpha z. And the other thing, I'm gonna get this stored as my radius. We said this was kind of the radius of this circle-ish. You know what I mean? Where I'm going to get this in my calculator as the radius. Because as a Mohr circle, this radius is that value anyway. You know what I mean? That value is that. And what we're going to see is that's going to be the max shear, is just that radius. And it's going to have a positive and this is the negative. This is going to be negative shear up here. This is positive shear. So it's kind of tricky for the Mohr circle. Alright, hell yeah. So let's input this into our calculator as the radius. So we have alpha a minus alpha b squared plus alpha z squared. Alright, so I'm going to store that as the radius. Okay, sweet. So, but yeah, let's do the inverse tangent of this. So inverse tangent of alpha z divided by alpha a minus alpha b. And that gives us an angle of negative 45. And so, theta P1 or theta P2, we're not quite sure yet, is going to be, and that's 2 theta P1. And so we're going to divide this by 2, divide by 2, and we get negative 22.91. I'm going to store that as alpha p. Okay, so now in this equation, if I do a negative here, no, never mind. No, it's the fact that this equation will repeat. Because it's a 2 theta, this equation will repeat itself. So if I do plus 180, that's going to be, and then divide by 2, that's going to be the second principal angle at 67.08 degrees. So this was the principal angle. Well, it's 2 times the principal angle. We add 180. You know, on this graphically, that's going to be the other. That's going to be 2 times the other principal angle. So both those would have to divide by 2. I'm going to store this other principal angle for the minimum. I guess I'm just going to store it as m. So alpha p for the max, alpha m for the minimum. And then I'll use alpha v for the shear angle. Okay, hell yeah. And now let's, like one thing that we can do is we can take this equation and just plot it into our calculator. And way to double check that we did it right is to also just know that, you know, we got this really fast just by saying, hey, we had x cosine squared plus y sine squared plus z sine cosine. Like, you can get this rotated equation so fast just by doing it like that way. So let's do this. And then in our calculator, this is going to be alpha a cosine x. Because even though this is going to be cosine of an angle, when I graph it, it's going to be a y, you know, something something x variable. So it has to be cosine x in my calculator. This is the TI-84. We're going to square that plus, and then the y value is my b in my calculator. So it's the cool thing about the graphing calculator of the TI-84 Plus is I can have any number of variables from a through z as long as they're not x and y. So that's why I use x and y as my a and b. Cool. And then we have sine x squared plus alpha z sine x cosine x. And I just want to make sure that these graphs overlap so I haven't made any errors. Here we have parentheses, alpha a plus alpha b divided by 2 plus alpha a minus alpha b divided by 2 times cosine 2x plus alpha z divided by 2 sine 2x. All right, hell yeah. And so we're going to, that's going to be negative 90 to 90. And so in between, anytime that you have an element and you rotate it in between, and this is 2 theta. Alright, hell yeah. Took a little break, but we're back. We got some more juice. And so what's going to happen is that if we're going to find our strains in the X and Y and the rotation with that Rosetta electronic strain gauge. And then we want to know where our max is. And so I'm just pointing out that max is going to happen in between a rotation of 45 and negative 45. So if we rotate our element 90 degrees, we will, and if we, so from negative 45 to 45, we are guaranteed to run across a maximum. I think that's true. We are guaranteed to run across a principal angle that's either theta principal angle 1 or principal angle 2. Yeah, so don't quote me on this, actually. So in between negative 45 and positive 45, you're at least going to have one principal angle, and you're going to have at least one angle that is the maximum shear. Yes, so that's what you're going to have. Now, whether that max shear is a negative max shear or a positive, because on the Mohr circle you could have a negative max or a positive max. All right, so cool. And I kind of took a little break, so I don't know where we're going to go from here. Oh yeah, hell yeah! We were graphing those 2 equations to see if they came out right. You know what I mean? Came out the same. And so this is going to be the strain in the rotated direction. And we're seeing, and we went from negative 90 to 90. I just mentioned negative 45 to 45. Well, yeah, that will be the angle of one of your principal strains. Will happen between negative 45 and 45. But what we're graphing, no, that's true. We're actually, what we graphed actually was, no, we graphed cosine 2 theta. Oh, that's fascinating. On one of the graphs, we graphed theta. And then on the other graph, we graphed, did we graph cosine 2 theta? Yeah, so do those graphs overlap? Oh, now I'm confused that those graphs overlap. Well, no, never mind. This is cosine 2 theta. It's still a function of theta. You know, our x variable still is theta on here, as in this equation, my x variable still is cosine theta. Even though this is 2 theta, I'm inputting the angle. You know what I mean? So now we can see that we have a maximum when our angle is negative, about negative 25. So we're going to go maximum, left bound, right bound. And so this is going to give us our maximum angle. So and this is going to be 2 theta P1 is going to be negative 22.915. That's going to be the angle on that. Now maybe I'm making a mistake. No, yeah, what am I doing? As I repeat, we graph this as a function of theta. Our x value is theta. So this is the principal angle at negative 22.9. That is going to give us the max value. Now the minimum value will be way over here on the graph. And so we're going to get the minimum value. And so this calculator is pretty cool because you can solve for zero values, you can solve for maxes, minimums, intersections, when slopes inflections points. And so this minimum is going to be at 67.08. So I don't need to do this by hand, but if I throw in this angle right here, well, no, let's do it. So that's the minimum. I'm going to alpha m, and we have that stored. And so graphed, let's do the minimum again, because it also gave me the value of it that I didn't really pay attention to. So the value is actually in my calculator stored as y. So we have this value stored as y. I'm going to store that as alpha h, just above the minimum, m and h. And then I'm going to go graph this. We're going to go value negative 15, value negative 30, and we're going to grab the maximum. So left bound, right bound, grab that maximum. Is stored the y value, alpha y. We're going to store that as the above p. So we're going to store that as alpha k. Hell yeah. So our maximum value is going to be 541 times 10 to the negative 6. And our principal strain, our minimum value, is it going to be a negative? Alpha h? Ooh, it wasn't. So let's graph this out. Yeah, so our minimum value. And then pay attention to significant figure. This isn't 660. This is times 10 to the negative 5. So this is 66 times 10 to the negative 6. And we don't pick up any, this is not 66.0. We don't pick up any extra, accuracy. And so, yeah, so again, strain, typically 3 digits are going to be used for strain on average. But it could have 4, and it could have 1. You could have 3. Your strain is a value of 3 times 10 to the negative 6. It's not 3.00 times 10 to the negative. You don't pick up extra accuracy. All right, hell yeah. And then so just by definition, our shear strain And it's kind of the way that we plot this, also the Mohr circle. And the reason we plot the Mohr circle like this is just graphically what the equations are doing. And we can pick out little slices of those to actually kind of get the Mohr circle started. Because this is going to be my shear in the x with a positive. So if I'm given, so again, A, B, and then Z. So if I'm given a positive, so my shear in the x, my initial, the points on here are going to be a positive. This was positive, this was negative, this was positive. It's going to be a positive, positive value, and that's the location of that. This point over here is going to be associated with the EY. Shear in the y is negative, and then we're going to have a, and at 90 degrees, the shear, so I'm going to say this is positive, negative, because at 90, the shear is actually going to be a negative value, and so it's going to be up there. And so that's going to set the radius. And so even just right there is that we have we kind of know the components. We know what this radius is. It's going to be the average distance between here, which is EX, strain in the y minus strain in the x minus strain in the y divided by 2. That's going to be this value right here. We're going to square that. And then we're going to add it to the initial strain squared, and then the square root of that. That gives me the radius of this circle. And so that is I'm trying to think why my radius isn't quite the same. I must be off by actually a factor of 2 on this equation. Yeah, I'm off by a factor of 2. I'm glad I caught that. Hell yeah. So even just right here, I know that this radius has to be the average distance divided by 2. It has to be this. So yeah, so that's just, I'm so glad I did that, because a lot of my videos are like make mistakes and then go find them. And I just wouldn't have found that because I haven't put any stock into this radius equation. Like my alpha r that I got, this is a wrong value. I think it needs to be just divided by 2. And so, but yeah, let's double check that. Alright, hell yeah. So this is the part of the videos that I really enjoy, because like you could either just kind of go back to see if you made an error, or, you know what I mean, try to redo this. Because the whole idea was to kind of practice figuring out what this max angle was, and it comes down to the derivative. And so, you know, we have this shear normal strain in a rotated direction. That's going to be the initial strain in the x cosine squared plus initial strain in the y sine squared plus our shear strain in the xy plane sine cosine. And then when we threw in the identities, this becomes x plus y divided by 2 plus x minus y divided by 2 cosine 2 theta. Plus, this is just one of these, it's not 2. So we have z divided by 2 sine 2 theta. And then we're going to take the derivative. When we take the derivative, this goes away. The 2 cancels. And so we're going to have x minus y. Cosine becomes negative sine. So we have this sine 2 theta. Derivative of this, u sub, we pull out a 2. Cancels that 2. We have a z. Sine goes to cosine. You know, sine graph is just cosine. So we just have a cosine 2 theta. This is equal to 0. I'm going to get this to the other side. So z cosine 2 is x minus y sine 2. I'm going to get the sine 2 divided by cosine 2 theta over here. Get that, and then I'm going to have z divided by x minus y. So no, we did it right. This is tan. This is tan 2 theta. So we have tan 2 theta is equal to our initial shear in the xy, strain in the x minus strain in the y. And that's exactly what we get. And so let's double check our radius. Our radius of, oh, okay, so two things are going on. This will have a, this radius, I'm wondering if this radius has anything to do with the radius of the Mohr circle, because the radius of the Mohr circle is the definition of max shear, where maybe this isn't, I thought this was that radius, but I could be wrong. So now to double check that, what we're going to do, and we need to go down that route anyway, is to solve for the shear in the rotated direction. And we do that by breaking out our element, and then rotating it. Yeah, let's grab another sheet of paper for that. Alright, hell yeah. So, I mean, for me, a lot of this, you know, I think you do hit walls. It's like, in learning, it's like, and even in this material mechanics book, I mean, I think by column bending, I think you just give up, because it's, I don't know, like every chapter is just worse than the previous chapter, just more difficult and just more involved. You know, this chapter 7, you know, hell yeah, it's hella difficult. Alright, so now we're just interested in the rotation of these two lines. That's the we want to rotate our element, but then see if it does this. And you really have to go back to kind of the preliminary chapters. When we have an element, and if we have an element, positive shear is where we have that going on, that. These two forces or stresses on, you know, it's still a three-dimensional cube. That's what we're analyzing. But those forces are balanced, but are going to cause rotation this way. We need to balance that, and that's the easiest way to show, you know, the forces or the stresses. The stresses are proportional in direction to the forces. And then what's that going to cause? Is it's and then the easiest way to draw this is to fix this point right here. But like I said from the very beginning, I don't know if that's the, I think you would want to fix the point in the middle, but you still have to have a convention to show the misshapenness, because these lengths don't change, but the whole thing kind of turns into a diamond shape. It turns into a, well, the volume turns in, I mean, it turns into a parallelogram from a side view. From a volume perspective, that's a parallel pipette. To draw it, fix this location. You know that, draw your arrows. Mess that up. Draw your arrows. You know that these are the two sides you're focusing on. This side will move up. So let's say it just moves up to there, done. This side will move to the right. You're kind of using the same thing with like superposition. But these two have to meet, you know, so I kind of just box it in and know that that location is right there. So this side moves up to there, this side moves over, but this corner has to meet. And so then just draw your shape. When the shape is like this is associated with a positive shear strain. And we get a change in angle there and a change in angle there. All we do is just tip this down so this side is resting flat. And when we rotate it this half angle, this angle doubles. These angles are the same in this picture. And then so if we do that, then we get that classic shape. And hell yeah. But just know that from consistency, these lengths don't change. So if these lengths don't change, sure, you're going to get a change in height, you know, total height. That total height's going to change for sure. But these angles are so small, this height change is negligible. So that change in height is negligible. Alright, booyah. The definition of shear is this angle right here. So that angle in radians is defining the deformation. And what's going to happen is on our shape, hey, like this part of the shape is going to maybe go that direction. This part of the shape is maybe going to go that direction. I don't know. Maybe this part of the shape goes that direction, and this part of the shape goes just hardly that direction. And we're gonna figure that out. And then it's you know, I mean, this went more that way, less that way. So still, this is going to be a negative. This is going to be associated with negative shear. If the angle gets reduced, this is going to be positive. Cool. So what we do is we have our this is dx, this is dy. I'm going to erase that because I rotated it up. This is dy, this is dx. Still, kind of make the same boxes. I'm going to make the box surrounding this dx, and then I'm going to make a box surrounding the dy. We're going to have a strain in the x direction. I'm just going to go out to there. And that strain is going to cause this line to now be right there. And so this angle alpha forms. I'm going to call it alpha 1 because it's just associated to strain in the x direction, which those are given. Strain in the x, strain in the y, and these are what we call plane strain. We do not have strain in the z direction. So all those little tidbits from you know, definitely texts have every sentence is juice, and some you just kind of gloss over. Alright, hell yeah. So this alpha is going to cause rotation that way. Maybe the strain in the y, which it will, check this out, if we just take this element, strained it in the y, is going to cause this hypotenuse to go that way. This is theta 2, and then if we shear it, you know what I mean, we're going to go this way again. And that's going to be kind of similar to theta 3. Just kind of equal as in the same direction. So what sign convention do you want to use? Because you can do whatever. There's no reason that you have to call these alphas. And then over here we're going to have the same thing. I'm going to just say positive strain in the x, y, and then z. So you know what I mean? That's what we're going to assume in the gamma in the xy plane. So, and I don't have to just show that it elongates that way, and I don't have to show that it equally elongates. I can just pick this side and say it bulges out that way. That's associated with positive shear in the x. This line goes to here, and the text call this beta. So, cool. And then if this shape went up like right here, hey, you would have beta. It's opposite of, you know what I mean? So that angle's opposite. One makes it go this way, the other makes it go that way. If we have a shear in this direction, well, that's going to be positive is this direction. And then so this diagonal is going to be over here, and hell yeah, now we're way over there. So we could say this is beta 1, beta 2, beta 3. Now, because I don't want to get into it for this video, because if you found a way to calculate, you know, this angle is part of the x prime direction. This diagonal is part of the y prime direction. And you can associate this y prime direction as just the x prime direction, where theta is theta plus 90. This x prime direction is associated with the angle theta, that initial angle of rotation. So if I can find a convention to show that these angles are a function of theta and then are in a particular direction, then when I come to my y, if I say this y1 direction is just the x prime theta plus 90, then I still have the same convention for my angles. And so that's why they do this as a textbook. They're going to say that angles going this way are positive. And if I get an equation for that, cool, I can figure out how much positive angle I get in that direction. But then when I take this equation and then everywhere that it had theta, I put in theta plus 90. Cool. You know, the sines become cosines. The cosines become negative sines. You know, not too hard. But the angle will still just be in this positive direction. So that's the best explanation I've done so far of why they have this convention of beta over here still being in this positive direction. Because if I wanted positive shear, I'd want to make this alpha this way, and these betas go that way. And so how we actually see how much positive shear we have is we have to add the alphas, and then we have to subtract the betas. Positive beta is this way. Positive alpha is this way. So we have to subtract those betas if that's... if we have positive betas, we have to say that's associated with a negative, like widening the angle is negative. And so if I have, anyway, so let's see if we can do that actually. I mean, I just said it, so let's see if we can pull out an equation for this angle theta, in terms of alpha, and then rotate it. And so, and then the alphas will become betas, you know what I mean? So alpha 1, 2, and 3 will be associated with theta in the x prime direction, where beta 1, 2, and 3 will be just associated with alpha 1, alpha 1 plus 90, 2 plus 90, 3, however you want to do it. Is theta plus 90 still in that x prime direction? All right, and so let's begin. So we have the strain in the x and the initial length. This element, once we rotated it, still has a dx as the dimension. And so I'm going to say this is dx cosine theta, this is dx sine theta. Oh, and then I don't even have to worry about this because we're going to try to use that convention and see if it falls out. This change in length is strain in the x, dx cosine theta. Again, that's a change in length. Strain is we're going to... whoa. We're worried about just the angles. But still, this dx will fall out if you do it this way. Okay, so this diagonal is dx. And we're going to say that's the radius of this line. And we're going to use the equation that alpha, so we have alpha 1 radians times radius. So we have alpha 1 dx is equal to arc length. You know what I mean? So we have radians times radius is arc length. And so if this extended out to here, we're going to draw in our rotated axes. And this is the hypotenuse. Strain in the x, dx cosine theta. What we're interested in is the sine component. And if we multiply by the sine theta, that is the arc length. That is the arc length s. So over here we have ex dx cosine theta sine theta. The dx's drop out and we have our alpha 1. Strain in the x, cosine theta sine theta. You could rearrange these, but if you write it this way, it makes more sense. You have your change in length, I see that component, and I'm taking a percentage of that in the sine direction, that's the arc length. Alright, so for the strain in the y, this is going to happen, and, what was our initial shape? Was our initial shape right here? I think our initial shape was right here, so we're going to have a strain in the y. This is going to go up to there, and then draw in our axes. So this component, it's the cosine component. So this change in length is going to be strain in the y, initial length, dx sine theta, and we're going to have the cosine component of it. So radians, alpha 2 times radius is equal to arc length. Strain in the y, dx sine theta, strain times initial length. and a percentage of that, a cosine percentage. Dx drop out, so we have alpha 2, strain in the y, sine theta, cosine theta. I haven't been paying attention to positives and negatives, so we need to do that. This caused a negative change in angle. That is where we're going to say that's the negative direction. So alpha 1 was negative. Positive strain in the y is causing a positive rotation. So this is going to be positive. Alright, so the shear strain, you got to use that radians times radius twice. This angle forms, and here's our diagonal, but here's our boxed in shape, and we know what's happening in this rotated xy direction, x, and then the y. Can't stress that enough. And when we have a rotated element, all we got to do is just box in the diagonal, and then we can see what's happening in that. So this box becomes like that, and we're just doing right there and right there. This distance right here. So this is going to be that arc length, where our radius is dx sine theta, and our angle is that. So angle, radians times radius is this arc length. So that is going to be radians times our radius is dx sine theta, and then that's going to be our hypotenuse. So that's going to shift this box over here. Our diagonal now shifts down. That's going to be associated with the negative. So we're going to have alpha 3 dx is going to be negative gamma xy, shear strain in the xy direction, dx sine theta, and we want here's our angle, theta, so we want the sine component of it. So we're going to have sine squared. Drop out the dx, and our alpha 3 becomes negative, shear in the xy, sine squared theta. Hell yeah. So now we have our full rotation. The change in angle of that diagonal x prime as a function of theta is equal to minus strain in the x. Now I'll just rearrange these. Sine theta cosine theta plus strain in the y. Sine theta cosine theta minus shear strain in the xy plane. Sine squared theta. And now we're going to try to find the change in angle in the x prime direction of theta plus 90. That is going to be the change in the angle of the y prime direction. This angle had a positive this way. If this term is a positive number, that's going to be associated with positive shear. If this term is a positive number, that would be associated with negative. So that's why we have the total shear in the rotated plane is going to be this minus whatever we get here. If I get a positive value for here, that's going to be a negative value for shear strain. And if I get a positive value for here, that's going to be a positive value. So what they would say is this your alpha minus beta. And this equation gives you beta. Beta is the total change of this diagonal. And whatever that number is, we have to subtract it from our alpha. This term is called alpha. And sweet. And how to rotate these theta plus 90. Pick an angle of about 10 and then add 90 and say, hey, that's the sine component and this is the cosine. This is the cosine component and this is the sine component. So if I want the cosine of, and this angle is theta plus 90. It's this theta plus 90. And if I want the cosine of theta plus 90, I know it's just the sine, but with a negative. So anywhere where I see cosine, I'm going to put negative sine theta. If I want the sine component of theta plus 90. It's this big length. It's a positive number, and that value is just equal to the cosine of theta. So sine theta plus 90 is just cosine theta. So we have cosine theta, and then this is cosine theta squared. Since it's squared, if I did have a negative, it wouldn't matter, and I don't because it's the sine goes to cosine. Yep, and so we still just have a negative gamma xy, and this is going to be cosine squared theta. So and this is going to be, all right, hell yeah. So ran out of juice, and I'll run out of juice pretty soon again. So this cosine goes to negative sine theta, and then I just my camera shut off, and I kept talking, and so what happens is that these two, the sign changes. This becomes positive, and this becomes negative, and this stays negative. But then I was just like, uh-oh. Well, and this is a negative sine squared, and this is a negative, cosine squared. So keep that in mind. But the fact that these two change signs, I was just like, well, aren't they going to cancel? And so it goes back to no. We derive this angle. If this is a positive value, that's going to be associated with positive shear. If this diagonal, the equation that we're coming to, is a positive number, then that means that it actually is a negative shear. And so that's why, even though this equation has the opposite sign, so we're going to have positive EX, and then, you know what I mean? Because all we did here was just sine goes to cosine, cosine goes to negative sine. So we get the same thing, and then just a sign change. Same thing here, just a sign change. So I'm just going to show the sign change. I'm going to keep the order of sine and cosine the same. And then we get two terms here, though, because we have minus shear strain xy. I'm sorry. We're just doing the rotated. So we get this. We get the shear strain xy cosine 2 theta. So this is my rotated element. And, this is alpha, this is beta. To get the total shear strain of that rotated angle, we need this and this. And we need this and then the opposite of this. So that is going to be this equation minus this equation. So now you can see that we have the same two things here. We're going to have a minus a positive. So we're going to have a minus a positive. We're just going to double down on that. So we're going to get negative 2 normal strain in the x, sine theta, cosine theta. And same thing here. A positive minus a minus. So this is positive plus a positive. So we get plus 2 strain in the y, sine theta, cosine theta. This is going to be a positive minus a negative. So it's going to be it's going to be this negative minus a negative. So it's going to be this negative added to that. Those negatives make a positive. So we have minus gamma xy sine squared theta plus gamma xy cosine squared theta. Alright, hell yeah. So we have our equation, and but it's still as a function of sines and cosines and the squares of sines and cosines. We can't differentiate this. I don't know if I'm saying that correctly. Like, obviously you just throw it into a differential solver. But if we do sine and cosine identities, you know what I mean? We just have to deal with sine 2 theta and cosine 2 theta. So, like, obviously anything is differentiable, but I think the second you differentiate this, I think you're just, using these identities anyway. Like, if you, I don't know, yeah, I don't know much, but I just know that, if you looked up in a differential table the differentiation of sine 2 theta, at the end of the day, and set everything equal to, you're going to get the same, yeah, it's going to be, you're going to get the same values. If you differentiate this and set it equal to 0, I don't know, but maybe it won't simplify. Anyway, so hell yeah. So let's recopy this. So we have, let's see if we can do it from memory. You know what I mean? It's always good for these problems. So we have the rotated shear strain in that rotated XY plane. And we're going to have, you know, it's going to be the accumulation. And one, you can always just start off from what we did. We took that rotated element and we had some strain in the X. That was associated with that length, you know, that cosine length. So we're going to have EX cosine. And then to get the angle change, it's that, what do we call it? The arc length is associated with the sine. So we have the strain in the X, cosine theta, sine theta. You know, so now we kind of have, oh, now I remember. And that's going to cause a negative angle change. So yeah, I remember that. We have a negative, and we're going to have 2 of those because the second we go over here. So we have a -2 strain in the X, and I'm just going to rearrange the sines and cosines on that. Sine theta, cosine theta. Cool. And then we're going to have a positive. Same thing's going to happen in the Y direction. Sine theta, cosine theta. Now over here, if I did rotate it this way, I'm going to have another length this way. And that's going to be associated with the radius, radians times radius. So it's going to be shear xy, the sine theta of that diagonal, and then that's going to be this, and then the arc length of it is going to be in the sine direction, and that's going to be a negative. So we're going to have negative shear strain xy. Sine squared theta. Over here, you know what I mean, that element is going to rotate this direction, which actually is just the positive direction. You know what I mean? So you don't even have to think of the alphas and betas. So we have our element, we rotated it, we want to know what's happening to this diagonal, we box it in, we know that we're going to assume a positive shear in the xy. That diagonal rotated this way, so it's just really cool just to, even without pen and paper, see what's going on. So at least it's going to be a positive. It's going to be associated with the arc length, so that's going to be xy. That distance is a cosine, and then so this distance is a radians times radius. It's this cosine, you know, of a dy, but that's going to cancel the, because anyway, so we have that distance is this cosine, and we just want to know the rotated, we want to know the arc length about the rotated reference frame, which will be a cosine of that. So we're going to have cosine theta squared. Hell yeah, so there you go. And let's see if we can do the identities from memory. We're going to have -2 strain in the X. This becomes 1/2 sine 2 theta. Hell yeah. So then we have +2 strain in the Y. This becomes 1/2 sine 2 theta. And then we have minus shear strain in the XY. Alright, so we better slow down because we have to recognize, you know, I already know this, the light bulb already went on. I'm going to do this as a plus, and now I'm going to factor out the shear in the XY plane. And so it's going to be, and then I'm going to have a negative sine squared theta plus cosine squared theta. I'm going to rearrange those. So it's going to be cosine squared theta minus sine squared theta. Now, again, like when people do trigonometry, they've already seen the light bulb before they're doing, you know, like the simplification. And so we can go over that one again. If this is theta and this is theta, this is cosine 2 theta. We take this as 1, and we say, hey, this dimension right here is cosine theta, And then let's take the cosine of it again with this angle. And this dimension right here. This dimension is cosine squared theta. We overshot it. So now we have to take this sine theta. This is theta. And then we're going to take sine theta. So this dimension right there is sine squared theta. Hell yeah. So now we can see that cosine 2 theta is equal to cosine squared theta, the bigger dimension, minus sine squared theta. So this one is almost like Pythagorean's theorem that should just jump out and pop at you if you ever see cosine squared theta minus sine squared theta. You know, if you ever have a cosine and a sine, even if you saw, because even if you saw this, let's say you saw, you know, let's say this was sine squared theta plus minus cosine squared theta, and you're like, ooh, it doesn't quite look. Well, just multiply. Do this. Yeah, this is what I've been. This is the math tip of the week. You know what I mean? If I want to manipulate the signs in this, just multiply by a -1 and a -1. Like, I don't know. I've never seen this in any other videos. I really don't watch a lot of math videos because I like to do it myself and make videos. Anyway, but hell yeah, multiplying something by a product of a -1 and a -1, hey, it looks like you're just multiplying by 1. So go for it. And so we're going to keep this -1 outside, and we're going to FOIL this bad boy inside. And then that way we get that negative sine 2 theta. This becomes positive. I'll just rearrange, do 2 steps at once. And you're like, ooh, hell yeah. And now I see the light bulbs on for this identity. So hell yeah. So this is just cosine 2 theta. And booyah. Now, obviously the 1/2 can factor out. And so it looks like we just have negative EX sine 2 theta plus strain in the Y. Sine 2 theta. Bummer. And then gamma xy cosine 2 theta. I didn't simplify it enough, but it's good to, you know, just show the steps. So now, because what they're going to do, I mean, this is exactly what I just did here. Like, hey, isn't that just this? You know, and I just factored out the 2 theta. Well, not good enough because they want the difference between the x and y. They want to take strain in the x minus strain in the y, but we, you know, so that therefore we do that same thing. Multiply, you know, have a product of -1 and -1, and then FOIL it through, and you're going to have a -1 outside. This becomes positive. This becomes negative. And yeah, this is the math trick of the week because that's where it came from. This is where I was using that trick because, you know, they're just going to show you in the book the equation looks like this. Negative strain in the x plus, bummer. Negative strain in the x minus strain in the y sine 2 theta plus gamma xy cosine 2 theta. So now this is the transformation equation for strain in the xy plane. I want to take the derivative of this equation with respect to theta and set it equal to 0. That's going to give me my max and mins. And the crazy thing about this is at any point we could just throw in this equation. So we have negative alpha a sine 2x plus alpha b sine 2x plus alpha z cosine 2x, and we're just done. You know what I mean? This graph will tell you all the answers to the answer. You know what I mean? So, but I'm just so focused on the proofs all the way through, so I just kind of know what's going on. And this equation is for the shear. We're going to have a max shear at a positive value. Well, we're going to have a and check this out. So our positive this value is going to be the biggest number. It could be a negative number, but it's just the largest value of normal strain. You know what I mean? If I have a huge negative number and then just a smaller negative number, this is my maximum normal strain. This is my minimum. This is the principal, second principal normal strain. This is the principal normal strain. On ours, it's a positive number, and it's associated with that angle, alpha p, which is negative 22.9 degrees. Now, honestly, that's plus 360. You know, from our rotate, if we're doing it from our rotation and we're rotating the right way, well, I mean, it doesn't matter. We've set our horizontal to be theta is 0, and we're setting that direction to be the positive direction. So it's just like going backwards on a number line. So I guess I'm chill with that. This is just the negative direction. But if I went all the way around to this negative 22.9, it would be 337 degrees. Because this next thing is going to say that the shear strain max, and because this is the max, oh, this is fascinating. If you have any shear strain at all, you're going to get a positive max and a negative max. I just realized that from the Mohr circle, you can't have any. If you have a point, you just have no shear strain. But if you have a circle, the circle is going to be on this axis where this is the rotated direction, and this is your normal strain, and this is shear strain. And the max and min are going to be the same value. So this is why, like, I want to do the proof all the way through and then start tackling the problems, because the problems are going to show a bunch of things like this where you're just like, oh yeah, the aha moments. But yeah, so sweet. And what we're going to find is that this is the max positive. This is the positive direction for that rotated shear, and that's going to happen always. You're going to take your angle, principal angle, and then subtract 45. So you could either take 337. You could take an angle of 337, which is that angle, and then subtract 45. So and I didn't go far enough because 45, and that's like 22 right there. So I could go all the way to here and then subtract 45. I think I'm going to be right there. So this angle is your max positive shear strain. And so the same thing is going to negative 22. And I'm just going to subtract 45 more. And so that's going to be a negative 23 minus 45 is 868. So this is going to be, so we're looking for an angle for 68. And that's, alright, so now we're going to differentiate this. Differentiating sine, so the sine goes like that, the slope is 1, that goes to cosine. The cosine graph, slope is 0, that goes to sine, but it's a negative slope, so that's going to be negative sine. So this goes to negative sine, this goes to positive cosine. And u substitution, the 2 comes out, and so we're going to have negative 2 ex minus ey cosine 2 theta. And then this is going to be minus gamma xy sine 2 theta. We're going to set that equal to 0. Hell yeah. I want to use my tricks, you know what I mean? Because I want to, what do I want to do? I have no idea. Well, does this work? I want to do this, you know what I mean? And then I'm going to, no, I don't. I just need to, oh yeah, so here's another trick. If I just don't want to write a lot, if this is equal to, I want to get this to the other side. And this is negative, just put an equal sign right here. Hell yeah, and just do that. Alright. I want to get this as a tangent, so I'm going to go cosine 2 theta. So that's down there. I need to get this to the other side. And then this will be tangent, and I just want to write it in this direction. So we have tangent of 2 theta. Don't forget that's a double angle. And it's going to equal, if this is tangent, it's going to equal this, which is negative 2 ex minus ey divided by gamma xy. And hell yeah, we did it. And what they're going to say is this is going to be, you put the negative anywhere, but we have negative, they're going to say this is this. EX minus EY, just to keep the same value here. And they're going to do this. This is gamma XY divided by 2. That's the same thing as putting the 2 up top. And to make this, because there's two different values, we could say this is positive normal in the X strain minus the normal strain in the Y divided by negative shear strain in the XY divided by 2. So this negative can be either top or bottom. Hell yeah, let me rewrite this. Cool, so we're going to rewrite this and try to rewrite it from memory. This is one where I am not good at, and this is tangent to theta S. This is going to be the max or minimum angle for the shear strain, and that's going to be a negative. The difference between the strains divided by the shear strain XY divided by 2. Hell yeah, now I got that from memory. You know what I mean? You should challenge yourself if you've already written it, not just to copy paste. It is good to develop some memorization skills. Alright, booyah. So now we're going to draw this on our XY. And the top, you know, just in general, this is our angle. Tangent is this divided by that. So tangent of this angle theta, and 2 theta is 2 theta, is going to be this divided by that. Yeah, so this is graphically, and this is equation-y. Alright, so we have a negative value for our vertical. So the vertical is going to be down here. We have a positive value for our adjacent. So cool. So we're going to be like this, going through that origin. And hell yeah. So now our opposite is in a negative direction. I'm not going to put the negative on this time. So we have just EX minus EY. Or maybe I do. Negative, but then parentheses. I never know what to do. Do you say it's negative? You know what I mean? Anyway, so then we have this is gamma XY divided by 2. And then same thing over here. This is going to be a positive gamma XY divided by 2. And this, oh, bummer, dude. This is a negative gamma XY divided by 2, and this is a positive normal strain in the X minus normal strain in the Y. So there you go. And I think this value right here is, I don't know. Yeah, don't quote. I just think if this radius is a positive value, I think that, and I just don't know. Let's say if the radius is a positive value. Because what we're going to do is we're going to put this into, and let's see if we got this from memory. Shear strain XY is going to be, oh, and yeah, I don't have this from memory, but hell yeah, do I know where it came from? Sure. The angle was going to be a 2 strain sine cosine plus 2 strain sine cosine minus a sine squared plus a cosine squared. Those are going to combine to just make plus 2 sine theta. So this cosine 2 theta. These are going to combine. We have is going to be the difference. It's the negative difference. The negative difference. So hell yeah. So I think we got it. We got the negative difference of sine 2 theta plus gamma xy cosine 2 theta. That is a difficult one just because it simplifies so much to do that from memory. And hell yeah. Alright, so the idea is we, and let's pick off this radius. It's going to be this squared. So I'm just going to do that, forget about the negative sign, plus this squared. And gamma xy divided by 2 squared. Alright, and we can, this you can factor out. This is a good one to do. Let's say you just had this term. Let's say you had the square root of 1/2 squared. You know what I mean? What are you going to do to that? You're going to multiply top. You're going to square the top, square the bottom. That's the first step. Then you're going to write those out. 1 divided by 4. No, you're not. Well, you're going to get to this step, but then you're going to realize, I think this is the quotient rule of exponents, where you do, I'm trying to get better at my definitions, but hell yeah, you can do that top and bottom. Okay, you know what I mean? 1 squared is just 1, square root of 1 is 1. This, you could write it that in one step, and then you could do 1/2. So literally this 2, and since this was 1, this could have, you know, you could have factored out, you could have done this, you could have separated this. So yes, also gamma xy divided by 2 is the same thing as 1/2 gamma xy. And gamma xy divided by 2 squared is the same thing as 1/2 squared plus this squared. And so we went through that whole, and then the square root of this is the same thing. So that's interesting, even if we're just looking at that term in particular. Oh, we're not though. Never mind. I thought I could factor it out. This side doesn't have one of those. So we would have to actually multiply top and bottom by 2. I think they do. So let's just not do that though. Because there's obviously little things that they do to make this look like the other radius that we solved for about an hour ago. Well, no, yeah, see, I still got this down to this is my radius, and I was satisfied with that. But this radius, I don't think was associated. We mentioned that this radius wasn't associated with this dimension. I don't think so. I'll have to go back and check that out. Where anyway, all right, let's try not to make any mistakes on this and see how far we get. So we have sine 2 theta. This is 2 theta. 2 theta s, 2 theta s. And where this is max is if this was 2 theta s. You know, this could be any angle, and you could get any shear, and it's going to be positive, negative. But if I throw 2 theta s in here, I'm going to get the max. So sine 2 theta s is going to be the opposite divided by the hypotenuse. So sine 2 theta s is this opposite. We have negative ex minus ey divided by this, which is ex minus ey squared plus gamma xy divided by 2 squared. Hell yeah. We're going to get a value for that, and then cosine 2 theta is going to be the adjacent gamma xy divided by the square root of the difference squared plus half of the initial shear squared. And let's plug off some values on these. Alright, so we're going to have negative negative parentheses alpha A minus alpha B. And then right here, we need to get this as our radius, or a new radius somewhere. We'll call it Q. Yeah, so this value will be Q in my calculator. Square root alpha A minus alpha B squared plus alpha Z parentheses alpha Z divided by 2 squared. Hell yeah, store that as alpha Q. Alright, so now we can get this value. Negative alpha A minus alpha B divided by alpha Q. I'm going to store this as alpha S for sine. I guess I don't need to, but I will. So we have negative 0.889. This is going to be alpha Z divided by alpha Q. Store that as alpha C for the cosine component, negative 0.915. Now again, these two values will be associated with the max shear strain and the positive max also, you know what I mean? Because the max shear and the minimum shear will be the same value, just because Moore's circle is like this. The max, if you have a circle like this, in this direction, the values are going to be the same. This is positive direction, this is negative direction for your shear XY rotated, and this is normal strain rotated. So principal 1, principal 2, those can be anywhere. One can be bigger. One's obviously going to be bigger than the other unless they're the same point. We don't have a circle. And then they can be anywhere along this axis. They could both be negative, both be positive, or split. But if I do have a circle, well, I mean, shear strain, positive and negative, is always going to be the same. Even if it's 0, it's going to be positive 0, negative 0. And the max is always going to be the same. But this angle associated with these two values will always chisel out the angle for the positive max shear. So that's kind of cool. Also, positive max shear is always the principal angle minus 45. So it's always minus 45. And that reason is because, let's say your principal angle is here. That's kind of the generic, like, I'm going to say, oh, never mind. No. Here is your principal angle. You know what I mean? So sometimes, just generically, this is going to be your theta is equal to 0. And maybe this is your theta is equal to your principal. Hey, my theta starting out could be theta is equal to 0 here, and my principal could be, like all the way around or negative. Think of it that way. And that's where I need to get better at Moore's circle. I really haven't played around with it. I'm just very fascinated with the algebra first and then dive into these. Because I swear just even graphing, a couple sine and cosine equations seem way more simple than going through all this work to get Moore's circle. But, whatever. But hell yeah, your positive is always going to be this down here because we said so. Because the equations say so, and so graphically, because we said so. Your principal angle is always going to be associated with this line, where, and your starting point really doesn't matter, but like from here, and then this is going to be right-hand rule. This is positive angle rotation. And so if I wanted to get to this, I would have to add 270, and that would be 270 divided by 2, which would be 135. Or I have to go this way, a negative 90. Because Moore's circles are always a 2 theta, type of thing, I have to divide by 2, and in reality we're just subtracting 45 from the angle. And so this value right here is associated with 2 theta s. All these values are associated with the 2 theta p, p1, your principal angle 1, and then 2 times your principal angle 2, you know what I mean? And then, so that's what the Moore's circle is, always 2. That's why you're going to make an error of 2 every time. But whatever. So anyway, you get your principal angle and you always subtract is because Moore's circle shows it, and why does Moore's circle show it? Because the equations show it, more importantly. Hell yeah. And so if you plug, and that's where I just don't know from a proof perspective, just in the books they say whatever value satisfies when you get this tangent and you get this ratio, you get this graph, and if you plug it into here, and you're going to use the this is going to be a positive or negative value, but it says if you use the positive value, so I'm just wondering if there's any chance of any equations where you actually have to throw in the negative value on this square root. You know what I mean? Like, that's what textbooks... I don't know. You know what I mean? That's where it's just like you're trying to follow the math to a point. And I still haven't done enough of these problems where the textbooks for sure say that if you get this ratio, And then we have a negative here. Who cares? Because this might be a positive or negative value. This might be a positive or negative value. And we have a negative there. And this might be a positive or negative value. But we do get a number and we get a ratio. Either a positive, negative number. And if we take the inverse tangent of that, we're going to chisel out an angle. That angle could either be the positive shear or the negative shear. And that's going to be the same deal when we take this tangent for the principal. So I need to go into the textbooks and see what they say on this, if some textbooks do a 1-2. Because this ratio alone, I think that's what they say specifically. This ratio alone will not give you popping out the right angle. The only way you can do that is if you solve for both of these values. But I just thought that was interesting, because if you solve for these values, it literally, can't you just stack these? I mean, literally, I don't know. I'll have to go redo that one and see why you would get a different angle on this one. Why if you plug in this ratio, you're going to get not the first principal angle, but the second. So that's the only thing I'm not up to speed on. And we'll just try it on this one. See if this one I'm going to get the negative. So, I should be expecting an angle of negative 22 minus, about negative 70. Alright, so we're going to take the inverse tangent. And don't forget, we're going to have to divide that by 2 once we do. So let's just do that right now. 0.5 inverse tangent of negative alpha A minus alpha B. Whoa. Divided by alpha Z divided by 2. And that gives me an angle of 31.38. Yes, so that is wrong. So this value is giving me the negative max shear. Where if I change the sign on this, no, I just get the negative value. So let's I'm going to store this as just a random, we'll store it as E. And maybe I made an error somewhere as well. Because we graphed it, and we know that this is our shear strain, so I'm going to go max. One of the commenters is like, when you get into the weeds, how can you double check your work? Well, there's always a very simple way to get your first equation. You didn't even need to get down here. We could have said that the shear strain, and let's compare, because we said it was negative 2 strain in the x, sine theta, cosine theta, plus 2 strain in the y, sine theta, cosine theta, minus strain in the xy, sine squared theta, plus strain in the xy, cosine squared theta. And we can visually see that, no identities, and then no further manipulation. So let's plug this in. Negative 2 alpha A sine x cosine x plus 2 alpha B sine x cosine x minus alpha Z sine x squared plus alpha Z cosine x squared. Alright, let's see if it just overlaps. Yes, we're overlapping, and booyah. Let that play out. Alright, so now we can find our maximum shear strain. Popping over to that graph. So we're going to go left bound, right bound. It's going to give us our value, so we can actually store that, but our angle is going to be negative 67. So hell yeah, so that gives me an angle of 67. We're also going to have a max, well, let's store these values. So we have x stored as shear, I'm going to store that as V. Alpha y, I'm going to store that as alpha w. So the max shear strain is going to be 488 times 10 to the negative 6. And I feel like I might have made a mistake. I don't know. Maybe I made a, did I make a mistake where I'm off by a factor of 2? I mean, this radius is just chiseled out from, a who cares perspective. I feel like, I don't know, why would I be off by a factor of 2? Yeah, I actually didn't look up the answers to this problem. Oh, no, hell yeah. Here's the answers. And yeah, now we're legit. Yeah, 488, that's the max. And 554 was the max in the x direction. And so I'm sure we got that right. Let me throw in some more juice. All right, my camera's about ready to die, and I need to recharge some more batteries. But we're going to come back to here. I'm going to go to value of like 25. And I'm going to do this minimum. I just wanted to know what this angle was. And this angle was 22.08. So I think, is this equation wrong even? That's what I'm thinking. Because I swear there's a divide by 2 here. And this just pops out where this radius is just this whole thing divided by 2. Because, and that would make sense. So that there is an error there. I can sense it. Hell yeah. Because this radius was, well, this doesn't have a divide by 2. Huh. Yeah, that's interesting. I just have to double check. I have to double check what's going on here. And hopefully I can find... I think it's because this was like a, I don't know. Yeah, where is my error? Well, here's the equation that we were trying to differentiate. When we differentiate, we get a negative 2. And then this pops out a 2. Oh, and so if we get it all to the side, we shouldn't have a 2 here at all. Maybe that's the deal. Oh, yeah, I think that's the deal. So I think, like, obviously I messed that up. I can just spot it right now. Like, this equation is legit. Yep. Like, I can sense that this equation is legit. And when we differentiate... Alright, hell yeah. So we're back, and for sure I made a mistake. And so, you know what I mean? So this ratio, we're going to double check. We don't think it's a square root of 2. So just by removing that 2, that should give us the right answer. And let's check it, because we said this was alpha q, and then obviously this isn't the max. So we're going to just remove that 2 and see if that does it. And then I'm going to talk about what they call the radius in these equations. Yeah, because that's kind of fascinating. In Moore's circle, this entire thing, if this is max, that is the radius of Moore's circle. Now, if we're... And that's when we have the rotated shear in that direction. If we're given the max principal, that's the principal strain right there and the principal strain right there. Well, the difference between those, this minus this is going to be that distance, that's the diameter, divide by 2. That's going to be the center of, yeah, the difference between these divided by 2 is going to be the radius. You know what I mean? So, so from both of those equations, you're going to get, yeah, so in the shear equation, well, what are we even doing? Oh, yeah, that's the bummer too. Is I'll have to look this up, because the only location they have this in the book, and this video's getting long anyway, so we can take a look at that. I know you can't see much, but you have to go back to the normal strain. In this gearbook, they only do it once for normal strain. And so what do they do? They get this ratio and they draw, yeah, where is that? They draw this picture, so for, and then they're calling that the radius. And yeah, I guess, is that the radius of Mohr's circle? Well, because the max shear strain is that. Yeah, so that becomes the radius of Mohr's circle. So for here, our radius should be this squared plus this squared square root that. But for this equation, for the tangent of this, we have a divide by 2. Is that... I don't know where that's coming in. Oh, yeah, it's right here. So, no, this is legit. So this is one side, and then that's the other. And that's going to be the radius of that. And then we have, this has 2 sides. But the radius is definitely something different. The radius is this divide. Oh, holy hell. Okay, so yeah, see, it's that factor of 2 that's going to mess me up all the time. Because the radius of this is just these 2 without this 2 down here. And that's cool. That's kind of what we were solving for. But that gives you the max. On the Mohr's circle, we want to graph that as half the max. Just so it's similar. I think they do it just so it's similar to the plane stress equations. I honestly don't know why they do it with that part. Dividing by 2, I mean, there should be big red flags of like, why are you doing that? But cool, so that's what it was. Holy hell. So this 2, hell no, that's not there. But this gives me the max. So the max strain is this radius, where when we graph it divided by 2, this divided by 2, that's why I kind of went through this whole rigmarole, because I knew there was something up. Well, to get this inside the equation, yeah, so let's do that one. Alright, so the max will be the square root of that plus the shear squared. So both those terms squared. This divided by 2 is this thing divided by 2. To get it inside, it's going to be, you know, I have to get this inside, I have to say this is the square root of 2, square root 2. Once I do that, then I can put this entire thing as this top divided by 2, oh, wait, whoa. Yeah, no, it would be a 4. Yeah, so inside it would be a 4. You know, cool. And then how do I get it inside these squares? Well, I need to say 4 is 2 is 2 squared. So then I have this plus this squared. And then I can say, well, that's the same thing as this squared divided by 2 squared plus this squared divided by 2 squared. You know, you're kind of doing the opposite of kind of separating it. And then this is the, you know, quotient rule or product rule. I mean, you think of quotient as products too, where of exponents, where this is this divided by 2 squared plus this divided by 2 squared. So that is where they're getting the fact that the shear max, and this is just another way to say shear in the XY rotated plane, but where it's max, divided by 2 is going to be the square root of shear in the X, the difference, shear in the X minus shear in the Y. divided by 2 squared plus shear in the xy divided by 2 squared. So that is going to be the radius. And that's going to be the radius of the Mohr circle. That distance. Alright, hell yeah. And shouldn't it have been very similar to ours? Yes. And so this is our radius. Now, why isn't this radius equal to... Maybe I made an error on this one. I don't think so, because we got the right angles. But yeah, why isn't this square root the same as this square root? I thought they were supposed to be, or for whatever reason. Ah, yeah. So yeah, back to my original conclusion. This is not the radius of shear max divided by 2. This is the radius of shear max. You know what I mean? This radius is associated with shear max. If you plotted on the Mohr circle, shear x1, y1, and that, then this would be your max shear. But what we plot on the Mohr circle is this. And that's for another day to figure out exactly why. Why did they do this divided by 2? Don't know. But when you get to this tangent, these ratios, and when you get to that square root, this is, I don't know, I'm just going to call it r prime because it's not the radius of the Mohr circle. You have to take this. This is the diameter. You would have to take this divided by 2. You know what I mean? So this value right here yields the diameter. And that's where my, I know enough about trigonometry, but it's really hard in trigonometry to just see things like the ahas, like, oh yeah, that's a geometric representation. And I know that's going to happen when using the Mohr circle and doing further problems. But my main focus was just the algebra to get to the proofs. And that's kind of what we did. And it's just fascinating. We really didn't make too many errors in this video. And yeah, we got everything right for the most part. Like here is the rotation in the XY. Here's principal stress 1. Here's principal stress 2. Principal stress 2 is just this plus 90. Max shear is just this minus 45. Max negative shear is principal stress plus 45. You know what I mean? And so, hell yeah. And what we should do, and then, so if the max principal stress, or if we have this stress, the max principal is going to be right there. The minimum is associated, so we have some sort of element. We're going to rotate it at some sort of angle where this becomes a max. So this is the strain in the, and this is going to be our rotated axis. And then this axis has our max, or our minimum. And so this is going to be, well, I'll just show it as the positive. But this will be a minimum. And at that point, the shear stress at those 2 points, shear stress is 0. So the shear strain, max shear strain is 0 at those principles. And so that's why we draw 2 different diagrams. And so when this is max, that's the angle we want. We want theta P1, and that's kind of what it wants us to do. And then we want, and then we're going to subtract 45 to get theta S, and that's going to be the max shear where it's going to be a positive value. And this is going to be, this could be a negative or positive. It's just the biggest. This is just the largest value at the first principle. All right, so again, let's just, just use our calculator to find these values. So we're going to do the maximum strain, normal strain, about a rotated point, and that rotation angle is going to be negative 22 degrees. And so when we draw our element, this is negative 22. Now for this, they want you to draw a box, unit 1 and 1. And I'm actually going to do my differentiation. There's no reason to call this dx dy. Just call it 1. And even though you can still have it as a rectangle, you can call this 1. So that means that when we do rotate it, I can just call this 1. And this value just becomes cosine theta. So I can even just put a C here and an S there. Over here, this is still 1, even though I just have it drawn, like smaller. Then this is theta, and then this can just become sine and cosine. And then so when I do the strains, then hell yeah, this is just x sine, and then yeah, booyah. It'd be x sine, and then you could figure out you just figure out the trigonometry easy. All right, so here's my rotated. This is going to be 22.9 degrees. And our strain is going to be a positive 554 times 10 to the negative 6. So let's go over to the lower minimum. And this minimum is a angle of 90 degrees away. And so that's what we should see. And so we have a minimum of 66, because it's 6.6 times 10 to the negative 5. It's 66 times 10 to the negative 6. And that's still a positive. And that angle is going to be 67 degrees. But I'm just getting these values because I've rotated my element, and so I found my principal angle. What did we know? That our shear is going to be 0. So this thing is going to, at this angle, is going to be hella out here in the positive, and then just up just slightly. So there. So what they would do is they would say, hey, this is my 1 by 1 box, and I'm going to do a dash line up. And then this dash line up has dimension of 66 times 10 to the negative 6. And because the length is 1, we always say change in length is shear times the initial length. But if initial length is 1, the change in length just is the shear in that direction. So this is going to be the principal, the second principal. It's also y prime at that angle, theta plus 90. And so, hell yeah, this is y prime, and this is the x prime, rotated negative 22.9. Anytime that I do like a negative, I think I'm just going to put parentheses just to be like, hey, don't do a negative. And then this distance is going to be 554 times 10 to the negative 6. So this is the 1 and 2 and the angle principal. That's what we drew there. We want to do, and we're going to take this angle, subtract 45. And, cool. And, because, oh, yeah. No, we're chill. I was just thought that within negative 45 and 45, within that 90-degree sweep, you would find a principal angle, and you would find a max shear. Well, sure, you can find a max shear, but it might be a negative or a positive. So here, our max shear is outside that window. Our positive max shear is outside that window. Also, there might have been the case that between negative 45 and 45 degrees, our principal angle, we might have found the second principal angle. So, this could have been rotated. The first principal angle might be outside of that zone. And, cool. But yeah, wait, is that true? So if I rotate 45 this way, and then negative 45, I don't know if that's quite true. Alright, hell no. So I even have this graph negative 90 to 90. So I would have, you know, if I rotate negative 90 to 90, I will be able to find a principal and one of the maximums. And if I rotate negative 90 to 90, I will be able to find the max shear. So I guess from these diagrams, I can either rotate from negative 90 to 90, and that just, I don't know, I guess that just makes sense. Because on this one, for the shear, we're going to be negatives. We're going to be, yeah, the max shear is over here at negative 60, you know, or negative 70. So this pink, this magenta line is the max shear, and that angle is this negative 22 minus 45. So yeah, so the max shear is negative 67.9 degrees. And so if we drew that on an element, I'm going to rotate down here, draw my element, and at max shear we do have a normal strain. So that value is x. And so we have normal strain. If I rotate all the way down here, we have a normal strain in this direction of 310. And I have to actually, you know, I need to, what do I need to do? So that red line is this right here. And I need to go theta plus 90. And so this blue line's the same, it's just hidden. So I'm going to go plus 90 on all the x's. And that's going to give me that rotated strain, the y prime. And so hell yeah. But yeah, to do these problems, you know what I mean, just find the rotated x as a function of theta, rotated y also as a function of theta, and then the shear as a function of theta. And you can actually do that quite easily, and you get something that looks like this, and I think this is more readable than a Mohr circle, because now we can throw in that value. I got one more graph to do. Alright, hell yeah. So now we can throw in this value of x. Ah, shoot. So let's do negatives. Let's get over there and let's do our maximum. Alright, so now we got that value. So, oh yeah. And no duh. Or where... Okay, so when the shear is max, the normal strains are the same and they're averaged. You know what I mean? So even just that, picking out those nuggets, like going through all that work, and just to be like, oh yeah, no duh, the norm. So yeah, the normal strain in this. So this is my x prime. And then this is y prime. So this y prime direction, my normal strain is also 310 times 10 to the negative 6. And then so to draw this element, the max shear is going to have a normal strain this way, and then a normal strain this way, and then we're going to have a positive, from this point, or we're going to have a positive shear. And so see how we draw this max angle in? And the way that we have our equation written in here is theta 1, or gamma x prime y prime, which is the shear in the rotated x prime y prime direction, and we do not have it as a divide by 2. So this does give us the max. On the Mohr circle, it's going to be that divided by 2. If you want the max, you actually have to take that number and then multiply by 2. Yeah, I never even thought of that. Holy Toledo. So on the Mohr circle, you know what I mean? This is your y prime, x prime, y prime divided by 2. You can get this value, but you best be multiplying by 2 to actually get the max shear strain. So yeah, I don't know. Yeah, it's like where you can just get the equations and then graph them, and you'll never run into a divide by 2, multiply by 2 scenario. Sweet. So that's going to be, well, and obviously this is the max positive because we said so. We wanted to find the max positive, and that's going to be theta P1 minus 45. That's always going to give you the max positive shear. If you go plus 45, that's going to give you the max negative shear. And that you can explain from Mohr circle, because this is the positive direction, and then angle rotations are positive that way. And so if I'm here at my principal strain and principal strain 1, then I actually rotate negative 90. This is a 2 pi circle, so that's going to be negative 45 degrees. All right, hell yeah. But here's the shape that it looks like, and so the final shape is up to here, over to there, down there. And we fully made it go this way and that way. So hell yeah, I'm just going to actually draw that in. So there's the final shape. And booyah. Alright, hell yeah. So we got the answer in the back of the book doesn't have the max shear. You know what I mean? So if we want to just come... Oh, and these aren't the right equations either. So let me look in the book. Might as well. You know what I mean? Because we can just... You know, it's also good to just kind of look at what equations are being used. And so, oh, those are the strains. Or no, I mean, those are the stresses. These are the strains. Okay, so our max, see this is max divided by 2. If I multiplied this by 2, these go away, you know what I mean? So, yeah, that's a royal bummer, this, but let's try it out, you know what I mean? Maybe we'll just throw it in the way they have it. So we have the square root of alpha A minus alpha B divided by 2. We need some hella more parentheses. Squared plus alpha z divided by 2 squared. Alright, get some more juice. Alright, so that is divided by 2, multiplied by 2, and we get 488, which was, you know, the answer on here. So let's go to a value of negative 70, go to a maximum right here. So this is the max shear. And we get a value of 488. 488 times 10 to the negative 6. The angle is going to be negative 67.9. And our value is negative 22.9. And what are we doing? The maximum? Yeah, so this angle for the principal strain was negative 22.9 in the back of the book, with a value of 554 times 10 to the negative 6. Alright, hell yeah, so we did it, you know what I mean? Did a lot of derivations, but booyah. And then once you actually look at these equations, then they just become more, you kind of see where they came from. But if you don't know where they came from, hell no. And even the fact that this is divided by 2. And even just this, like I haven't even covered getting this in terms of that radius. Like that requires an algebraic manipulation. That's the only one that I haven't covered. It's kind of a fun one to do. It's just but anyway. So I think we're done with this. Thanks for joining me. Hell yeah.